CSC for high priority simulation projects, and they were allocated to 28 projects selected by the EU-JA Joint Allocation Committee. And this time, we have 6 talks and 3 from EU projects and 2 from JA projects and 1 from EU-JA joint project. So yeah, this is the agenda of the workshops. So important notice, please be aware that photos, screenshots will be taken during the workshop, and this workshop will be recorded by the function of yeah, recorded by a function of MS Teams. And yeah, such a video and video will be publicly shared on Eurofusion website, and screenshots and photos will be uploaded on the QST website, Eurofusion website, and IFERC websites later. And also, these are used for IFERC, Eurofusion, and QST communication materials. Okay. Yes. And the chairperson of this workshop is Yagi-san, a member of the Joint Allocation Committee. So Yagi-san, please take over.
Okay, so just let's start the sessions. So first speaker is from Japanese side, Dr. Matsuyama, integrated simulation of disruption mitigation runaway electron in ITER and demo. So please start.
Okay, can you hear me?
Yes, I hear you.
Okay, so I'm not sure if I should the camera video on, but okay. Good morning, European colleagues, and good afternoon, Japanese colleagues. And my name is Akino Matsuyama from QST, and this work is a collaboration with Dr. Yamamoto in the same institute. And the title of it is Integrated Simulations of Disruption Mitigation and Runaway Electrons in ITER and Demo. The project acronym is INDEX-BA. Okay. So let me introduce, and there are some issue which we are addressing. You know that the disruption mitigation system is a key plan to ensure successful operation in ITER and beyond. And this is a famous figure that shows the parameter space of the ITER operation in the space of the plasma current and the thermal energy. And with the enhancement of the plasma performance to the higher current and the thermal energy, the machine load associated with the disruption becomes much bigger and bigger. And I do not go into details of this figure, but I can emphasize here that only the small portion of the ITER operation space does not require mitigation of the disruption, but in other parts, especially in the high plasma current and the electromagnetic load mitigation is very essential, and also for thermal energy. And let's say the final target of the DTH mode has the magnetic thermal energy about 350 megajoules. This is the far exceed from the melting limit of the diverter and the fast flow. So to have a reliable mitigation in this final target, disruption mitigation system have to be commissioned from early operation. And this commissioning is even essential for the routine operation towards the achievement of the mission goal of the ITER. So this research is very important towards the ITER. And so let me introduce a bit about the early result of our index project. And we started a bit on some MHD simulations. And for considering disruption mitigation, what is difficult is that the disruption mitigation that is not optimized is even harmful because it injects some impurities into the plasma. This leads to the enhancement of the radiation. And this example shows the simulation of the radiation-driven disruption by introducing the argon, very much argon, into the plasma. And this triggers the perturbation to the magnetic perturbation associated with the current profile change. And this to the thermal collapse. And finally, the current quench leads to some significant generation of the runaway electron. And this is a movie for the simulation of the temperature, current density, and the runaway electrons. And by introducing the argon, plasma edge is significantly cools, and this leads to the current perturbation. And this finally leads to the thermal quench. And after the thermal collapse, in the plasma, the strong electric field is induced, and especially at the plasma center when the plasma center. And this strong electric field can drive the runaway current, especially in the relatively slow time scale associated with the avalanche amplification associated with the close collision between the high energy electron and the thermal electrons. And finally, such a significant beam compared to the initial plasma current can be carried by the runaway electron. And if you have a vertical displacement of such a beam, the impact of such a runaway electron may have a significant energy load to the investor component or the plasma facing component. So anyway, so the message is that disruption mitigation must be optimized well to avoid such a event, but we still need to introduce the impurity in order to control the other loads such as the plasma thermal load and also the load associated with the electromagnetic energy such as the plasma current and the Haro current. And based on this importance of the research, we are starting the project. We are continuing the project for the research on the disruption from the age of the IFERC CSC Helios and from the 2012. And in the early simulation phase, let's say the BA phase 1, we have focused on the simulation of the phenomenology, let's say the thermal quench, vertical displacement events, and the runaway electron generation, and so on. But today I will talk more on the second part of the BA phase that was carried in the being carried in the BA phase 2, the project index BA, and also this is also related to the demo design activity. And our focus is now pressed more on the designing the mitigation scheme towards the ITER and demo. And this has a direct link to the ITER DMS task force and the JEU joint demo design activity. So today I would like to talk about this second topics and the highlight of our recent results. Okay, this is outline of my talk, and the first part it is the recent result of the disruption simulation in support of the physics validation of the ITER disruption mitigation system. And the second is the development of runaway electron simulation for EUJ joint activity on the characterization of the runaway electron wall load in demo. Okay, can't see the time, but okay, let's see. Let's try. Okay, so the numerical code used in this work is the index. This is the integrated simulation code for the disruption. And the model is very simple. And the core plasma is relying on some 1.5D tokamak model. But the key feature of this code is that the code can couple to the external circuit with some iteration of the Grad-Shafranski equation and the external current circuit equation. And this allows the self-consistent simulation of the VDE and current quench model. And in the right figure, some schematics of the numerical scheme has been shown here, and the right one is a benchmark with the famous DINA code that is used for the disruption modeling in ITER. And this is the benchmark of the plasma current and the vertical position of the plasma during the disruption, and especially the upward VD case for the ITER. And so using this code, what we have done is to implement the modeling of the shattered pellet injection. You may know that this shattered pellet injection has recently been determined as the baseline of ITER DMS. And in this scheme, the large cryo pellet, which is almost the size of the wine bottle cork, is injected into the plasma. But before the injection, they are shattered into the small fragments, let's say about 1 or 2 several millimeters of the size. And such many shells are injected into the plasma like in this way. And in this simulation, each shell is tracked as a marker particle in the simulation, and the aberration of these small fragments has been calculated by using the simplified modeling of the aberration, and taking account the simulation of these particles. The simulation has tried to track some plasma time evolution of the plasma profile and the current profile to evaluate the let's say the electron density profile that is important for random electron mitigation, and also this change of the electron temperature and the impurity that is of course important for the evaluation of the thermal loads. And using the feature of the index code, the code can also track some evolution of the plasma current and the vertical position. Such a feature can also be used for the evaluation of the electromagnetic load in the device. And one of the recent achievements is the benchmarking with the JOREC. And the JOREC has widely been used for the simulation of the SPI experiments or in many tokamaks such as JET and K-star and K-star, and we have focused on the benchmark between the code, and we have achieved a successful code benchmark with the JOREC asymmetric SPI simulation for this standard pellet for standard pellet composition for ITER in the 50 megaampere hydrogen aero mode case. And the bottom is an illustration of the example, and the top is a 500 meter per second case, and the bottom is a 200 relatively slow injection case. And you can see the dashed is the JOREC result, and the solid curves as the index. And this shows the evolution of the neon density after the injection of pellet from this side, outside of the plasma. And you can see the deposition of the neon into the plasma. And such a deposition can lead to some cooling of the plasma, and also the increase of the density to avoid the runaway electron. And the right figure is the time trace of the aberration rate and the radiation power. And you can see a relatively reasonable agreement of the aberration rate and the radiation power between the code. Such a basis has been built up with the help of this IFERC project. And so based on such a benchmark, we have studied some parameter scan of the ITER operational, ITER parameter space of the SPI design, parameter space of the ITER SPI design. And this is the scan of the pellet composition, magnetic field, and also in the space of the pellet velocity. This number n represents the size of the small shells of the SPI, and here the large n number represents the small shell case, and you can in this operations in this scan we have evaluated the time required for the plasma, time required the SPI to cool the plasma near the Q=2 surface. This is the indication of the thermal quench trigger time. And you can see the variation of the thermal quench time depending on the size of the pellet shell size and also the pellet injection velocity. And this blue hatched region means the time before some plasma reached to the the time for the pellet charge reaches to the plasma center. So this white region means the parameter region where the pellet can reach the plasma center before the thermal quench happens. This means this white zone is a very optimum to laser density for the runaway current avoidance. And such a parameter space has been investigated for a different parameter using the index code, and this has been a good basis for the design of the ITA DMS. And these results have actually been inputted, has been provided for the ITA organization for the design of the ITA DMS. And we are now currently doing more work on the pellet and SPI physics to strengthen such a physics basis for the ITA DMS design. And we believe this is a good contribution to ITA. Okay, another technical aspect related to this index PA is the IMAS implementation. And you know that IMAS is the standard tool for the ITA to store the database of the not only the experiment but also the modeling results. And actually, our group is now in charge of the implementation of the task agreement with ITA organization for the ITA DMS simulation. And the scope of this work is to provide the ITA organization with the modeling of the shattered pellet injection and to support the definition of the design parameter of the DMS. And to effectively implement this project, and we are collaborating with the IFERC CSC to implement the IMAS interface into our code. And the prototype of the interface has already been developed, and we are now preparing for the production run. And we believe that the simulation data will finally be provided to IO through the IMAS infrastructure when we submit all the data to the ITA organization. Okay, so the next is the second topic, more related to the demo, and this is the simulation of the random electron for the JA and EU demo to characterize the runaway world load. And let me briefly introduce the topic. And actually, disruption load specification is a very important and the key element for the demo design. And to proceed the demo design, analysis of the plasma transient, taking into account both the unmitigated and mitigation disruption loads, is a very important database for demo design. And especially I believe that this data is essential from early phase of the demo design activity in order to build up a basis for the safety, commissioning, and operation scenario and the investor component design. And with this aim, and in the demo design activity of the IFERC and the project task 1.2, evaluation of the plasma facing components heat load during a transient has been specified. Oops, I'm sorry. And the purpose of this work is to build up a strategy to allow the protection of the foreseeable against foreseeable and unforeseen plasma transient via the installation of the discrete and the possibly sacrificial limiter. And this is the right figure shows the example in the EU demo design. Like this colored limiter, you can see some design of the colored limiter. And so for this evaluation, we started the project to evaluate the runaway electron load using this IFERC CSC project. And let me briefly remind you some mechanisms of the runaway electron generation in tokamak plasmas. Runaway electron generation has progressed in the plasma, in tokamak plasma in two stages. First is the seed electron generation, and this seed is exponentiated by the cross collision, so-called the avalanche amplification. And in the device like ITA, plasma, the fraction between the ratio between this seed and this primary electron, the secondary electrons, strongly depends on the plasma current, especially that this secondary electron generation becomes important for higher plasma current devices. And other difficulty is that the seed mechanism of the seed generation is very complicated, and there are several mechanisms to trigger such a seed generation. For example, the Dreiser acceleration is well known, and not only this one, there's some transient deformation of the electron distribution function can trigger the seed electron, so-called the hot electron. I can illustrate here this. And when the plasma is cooled very much fast due to the introduction of the impurities, such a significant deformation of the distribution function occurs. The tail of the electron can be accelerated due to the electric field associated with such a cooling process, because the speed of resistivity depends significantly on the temperature, and so such a cooling can lead to the acceleration of the tail part of the electron distribution function. And in addition, this is a fundamental difficulty in the nuclear phase, and in future ITER and demo devices, when the DT operation is in the case of the DT operation, there are steady high energy electron source such as the tritium decay and the Compton scattering can occur. And for these seeds, the number of electrons generated by these mechanisms are very small, but because of the huge avalanche gain expected in the ITER and demo, such a seed can be a problem to trigger the random electron beam during the disruption. And in principle, this seed is difficult to be eliminated in principle. So we have to always be very careful to have a random electron beam in future devices as compared to the existing devices. And to simulate such a random electron generation, we started from the kinetic simulation of the random electron generation. And this is an example of the simulation of the random generation. And let me try be more quick. And the left figure shows the time evolution of the distribution function without the avalanche amplification, and the right case that takes into account avalanche. And the simulation starts from this seed electron in the relativistic regime. And if we do not have avalanche amplification, this seed just accelerates to the high energy, and such a seed can decelerate it to the low energy. But if we have the avalanche mechanism, this seed can trigger the random electron from this seed can scatter the some electron to the random energy. So as a result, this can lead to this kind of the exponential tail in the high energy region. So this can be dominant mechanism for random electron generation during the disruption. And the growth rate of this tail is very important quantity to characterize this random generation in ITER. And the right figure shows the benchmark of the avalanche growth rate using the JFRS1 as a function of the electric field. And this dashed line is some classical Rosen-Bruce formula. And recently, more refined formula has been proposed taking into account the atomic process between the relativistic electrons and the partially ionized ions. And you can see that this black and white points are our calculation based on the kinetic code. And our result are very good agreement our result are in good agreement with the recent result by this Fokker-Planck code CODE published by the linear Hess law. And based on this activity, we have used this kinetic benchmark result is used to define the simplified random electron model. And so based on this result, we have improved the accuracy of the simplified random electron model that can be used for the integrated simulations. Okay, so this is such a slide, and in the integrated simulations, the large-scale kinetic simulation is difficult to implement. But if we now have a relatively good model to simulate the random electron using a simple formula, and this is the Okay, so this is a bit small topics, but in this cycle, we have implemented the random electron source model into the index code, including both the primary random electron source and also the secondary avalanche generation. And as I have shown in the previous slide, and the avalanche growth rate and has been benchmarked with the kinetic. We have implemented the simplified modeling benchmarked with the avalanche growth model based on the kinetic simulation. And okay, this is a bit small things, but yeah, and we have successfully implemented, and we have also performed the benchmark of this simplified modeling with other code, so-called European code Go. And this is a benchmark simulation of the random electron generation with a different fraction of the neon and the deuterium in the plasma. And from left, this is the current, electron temperature, profile evolution, and the current density. And you can see the good agreement with the Go code and our code index for the time trace of the plasma current, and also the other profile for different setup of their impurity content in the plasma. And so this was the first topic, and the next topic is to simulate the VDE in the demo. And this work has been done in collaboration with the EU colleagues, and this is a simulation of the VDE for EU demo. And we have benchmarked our index code with the Kinetic code in EU. And this is the benchmark of the initial equilibrium for the EU demo. And this is very not. And the maximum difference in the CF coil is only about 80 kiloampere. This is less than 1% of the maximum coil current carried by one PF coil. And you can see the plasma shaping, profile, pressure profile, and the safety factor profiles are very reproduced. And using this initial equilibrium, we have compared the simulation of the VDE and the EU demo for some specific scenario proposed by the EU colleague. And this is the time evolution of the plasma shaping during the VDE and the thermal quench. And you can see that this red curve is the last close flux surface provided from the Kinetic code, and the blue is the index code. And you can see a relatively good agreement between the code for the time scale and especially the contact point to the wall in each time of the thermal quench phase and the termination phase. And we believe that this is a good reference data for future simulation to discuss the plasma disruption load in demo in future analysis. Okay, so this is the last slide. I'm sorry, this is the last slide. And we are now implementing the work plan for evaluating the disruption load in demo in close collaboration with the EU. And this is the work plan during the PA phase 2. Now we are in this first phase, and we have made a code adaptation to implement the runaway model to index and the comparison the VDE between JA and EU. And we are now working very hard for the analysis of the VDE with taking into account the runaway beam generation. And so the final goal of this work is to analyze the MHD stability of such beam. Because this left figure shows the observation in JT60U, and in the JT60U, during the termination phase of the runaway beam, the MHD activity associated with the external kink mode has been obtained. So we believe that this is the cause of the runaway wall load, and this can dominate some, let's say, the toroidal distribution of the runaway electron loads to the wall. So our goal is to evaluate such a MHD stability and the runaway wall load by coupling the index code with the orbit following code. And these data will be provided to the EU colleagues, and they can analyze the volumetric heating of the wall by the runaway electron using the Furuka code. And our final goal is to couple to perform the whole the workflow starting from the BD simulation with index and analysis of the wall load by the orbit code. And this code can provide the information to finally evaluate the volumetric heating of the wall by the Fluker code in both EU and JA demo. Okay, so let me summarize my talk. And our project Index BA has made a big progress on the disruption analysis and ITER demo. And the first part was related to the ITER disruption mitigation system. And especially the IMAS development of this project has been supported by the IFERC CSC. And the second part is the demo relevant development in the cross collaboration in EU and the JA demo, and we hope we can have a much more result in next occasion through the collaboration in this IFERC CSC. Okay, thank you very much.
Okay, thank you very much. Now, the question and comment. If you have a question or comment, please turn off the microphone. No questions? Okay, so I have a questions. So you compare to simple 0D model and 1D your model and also JOREC simulations. And what is your prospect compared to these three models, like 1D, 2D, 0D models?
Okay. So you know very well about this comparison. I didn't emphasize this comparison, but this is one comparison. We are now working on the comparison between JOREC and the 1D index, and also we have to interpret the result. We have also performed the analysis of the 0D model to understand the physics process. But if we change the composition of the neon pellet, of course, in some cases, this 0D model does not work. And even the index, in some cases, approximation may be worse. And even the JOREC, and JOREC has a limited spatial resolution for the pellet physics, actually. And the pellet physics has to resolve the very narrowed, localized pellet cloud. And we found that this is very difficult to resolve by JOREC, actually. And but anyway, so our intention of this work is the design of the ITER DMS has to be complete before the 2023. And anyway, we have first would like to address the whole parameter space by using the simplified code. And we are now in the phase of the scoping study using the different modeling. And we hope finally we can go better model. But this requires a huge computational resource. But we are in close collaboration between the different modeling levels, and we are collaborating very closely recently with the JOREC colleagues. And so we hope that this activity can put the things forward.
Thank you. Any other questions? No? Okay, so if no questions, we proceed to the next speakers. Thank you, Matsuyama-san.
Thank you.
Okay, so next speaker is from EU, Dr. Chakaya, report from project HD6. Please start.
Okay, I'm trying to start, but so. Okay. So, good morning and good afternoon, everybody. I will speak today. So, first of all, let me thank organizers for giving this possibility. I was thinking about collisional schist model, which was developed and based on the simulations performed under IFERC project, HT schist. And I want to acknowledge support by ISFN, so ITER Scientific Fellow Network, this whole group, with whom we had very useful discussions. So most of you probably know that there is a very narrow layer of plasma which forms at any plasma device in front of the wall. And this is especially important for fusion devices, where this layer kind of governs plasma flux, heat loads, and also is very important for the measurements because it defines of the potential drop between the plasma and the wall. So these are very simple expressions which are given here. And as an example, if this plasma schist can be formed, mainly most important area is diverters when you have the highest heat loads. And we can see that all these expressions depend on the parameter, which is a parallel Mach number. And existing classical model of schist means predicts that Mach number is equal to 1 at the schist entrance.
Sorry, Dave.
Yes.
Are you sharing the right desktop? Because currently we see the presentation in the sort of slide view mode.
Oh, okay. I think, so you don't see the introduction now?
Now we do, but previously it was still showing the thing and it's not in full screen.
Is it now in full? Because I see it's in the full screen.
Then you probably have two screens and you're sharing the wrong one.
Okay, so sorry. Just let me go back.
Maybe once you.
I will stop sharing.
Yeah, and try again. Maybe
okay. Window.
Display. Yeah, you share the display, and then the power.
Oh, there is the entire screen.
Yeah, entire screen.
Share. If I share entire screen, then I don't see my. Okay, I don't see my
PowerPoint. You don't.
Okay, just. Okay.
You're calling there.
Yeah. Okay, if I share window, it does not work as I see. Yeah. So, do you see now full screen?
Not the full screen, but it's just the PowerPoint, but not full screen mode.
Yeah, okay.
It should be okay.
Yeah, okay, last try.
Yeah, we can continue the present, the
okay.
Even so, it's not full screens.
Okay, if I try to do entire screen, nothing comes out. So, okay, let me come back. Okay, so, yeah. No, this is. Okay, so yeah, I tried. Okay, I think at least you can see non full screen, but let me go. I will also put. Okay. Sorry for this, but let me continue with this and once more mention that all the important parameters which define particle heat flux to the wall as well as potential drop are defined dependent on the so-called Mach number, which is from classical model is 0. Now, we made some kinetic modeling, very precise kinetic modeling for existing machines. It was published some time ago. And we find out that the position of this point when Mach equals 1 is exactly in agreement with the classical model in few INJ radii. And it was quite good result. And until we continue increasing density to come to eta-relevant densities. And we find out that then this model doesn't work anymore, because in most of cases, Mach number equal 1 never satisfied, or it was satisfied very near to the wall, so well below this what was predicted by classical model. So, and there was a problem. So why? And now to realize why we have so different conditions for existing machines and high density machines like ITA and demo, one has to consider Schiss model, so classical Schiss model, and also what are the conditions in the next generation machines. And there are a number of conditions you have to satisfy to have Schiss model, but I consider just most important for us that ion gyre radius should be much smaller than mean-free pass projection to the normal to the wall. In other words, Schiss is collisionless. And this is very basic condition which is used in derivation of classical model. And if we now come to different machines, we find out that with increasing machine size, these parameters of plasma sheets become more and more dense and more cool. So it means its collisionality of plasma in the diverter region becomes more and more collisional. The question is, are these conditions satisfied in larger fusion devices? And for this, we can consider the following graph. This is density, this is temperature, and we can use some assumptions like cutting out too high heat loads to the diverter, too high pressure in the outer mid plane, and we find out that the classical Schiss parameters of classical field conditions will be satisfied here. There are some other regions, but most important, so collisional region stops in this yellow area. So whenever I have high densities and low temperatures in this area, you do not have any more classical Schiss, so mean-free pass is becoming smaller than ion gyre radius. Moreover, if we continue this increasing of density and temperature, we even cannot use a classical model of the plasma, and we have to account also quantum mechanical effects. But fortunately, in this area, so it's sufficient. And we find out that, okay, so the one possible reason why we have different conditions at the Schiss entrance is that Schiss is not collisionless anymore. And in order to study this effect, we consider particularly in cell model, BIT1, it's electrostatic 1D3V. It has, so geometry is given here. It's quite simple. It's considered it's a flux tube code. This is a plasma bounded by two diverters. You have a particle source and heat source in the middle of some area, and then particles propagating towards along the magnetic field towards the diverter plates, and then you have plasma recycling and sputtering of impurities. And this is a quite large set of physics, I mean atomic and molecular and plasma surface interactive processes, which were implemented in the code version which was used for this project. In the new version, we have much more processes, but for the plasma or Schiss simulations, this was more than enough. It's important that it has nonlinear model between plasma, neutral, and surface, so it will self-consistently reproduces physics, which is necessary for the plasma Schiss. It's massively parallel, and as you will show at the end, it's quite time-consuming even for simulation of the plasma Schiss. And this code was used under the project. We simulated quite a large set of simulations. I want to say that this was actually spread in two projects. During one project, we obtained, as we thought, the main results. So we consider increasing density and included more and more physics. So we started with low density, so no recycling, so no neutrals, and moderate density, and then increased it. Also, we had initially we had only plasma, no plasma recycling, then plasma recycling, then we included molecules, and then we included also three-body recombination. So all physics which we could do with this code. And this is one of the examples of simulation. So here's a density of different particle species, neutrals, as well as the ions. And this is the diverter plate. So up to here, we mainly job was done. And we are quite happy because we really saw what we expected, which is given here that if you have the low densities, your profile of the Mach number shows that really your Mach number equal 1 is satisfied, is low density plasma. or moderate density plasma. But whenever you go to high densities, so here's a diverter, here's a distance from the wall in ion gyralysis, you see that it never reaches Mach number wall at any point. And yes, so we find out also from this more precise simulations that Mach number 1 is not satisfied. And there is questions, so why we are getting this? So what is the reason? Okay, we know that these are collisions. Question is which collisions and why? So what is the border point? Then we can say that we have classical sheaths and we otherwise not. In order to do this, we did numerical experiments. First, what came in mind that when we have a collisions, we have a diffusion. Let's say diffusion with neutrals, with interaction with neutrals, and so on and so on. But we excluded this immediately because we consider total path flux of particles to the wall and then compare with it with the just convective flux. And we find out that, yes, we have a very small contribution of, let's say, diffusing one, but it's just, let's say, less than 2–3%. So it means that this diffusive flux is cannot be a real contributor to the increase of the Mach number. So to the fact that Mach number, so plasma is not sonic anymore. And then with another set of experiments, we started, the advantage of code is that you can switch off different processes, and we started to switch off processes step by step. So we excluded electron-ion collisions, ion-ion collisions, electron-neutral collisions, and find out in none of these cases we get a Mach number equal 1. Only if you switched out the electron, so ion-neutral collisions, then we got back to the classical sheaths. It means that actually the real reason of this new property of the sheaths is not Coulomb collisions, but is collisions with neutrals. Now, the question is why this is happening. Let's explain this physically. If you consider that ion moving near the wall, so we can distribute, I mean, we can consider two projections, normal to the wall and tangential to the wall. The tangential, the force along the normal to the wall has three components. One is electric force, and two, the friction with neutrals and friction between electrons and ions. And all of them are directed, so, I mean, let's assume as a beginning that we have positive current, and we see that the frictions are against electric field, but the ambipolarity requirement requires that electron and ion fluxes should be equal. So this means that the electric field should be adjusted in a way self-consistently that you still get that normal to the wall component of current is equal to the electron one. So we can write this expression here. On the other hand, in the tangential direction, there is no electric field, of course, in one-dimensional approximation, and they have only friction. So it means that in this direction, your velocity will be less than in collision-less classical case. This means that if this component is classical and this part is not, it's clear that you never get the sound speed equal 1. On the other hand, there is another point that if we have a negative current to the wall, situation can change. If you took a very strong negative current to the wall, let's say we have very electron current dominated regime, so electrons could, due to friction, take ions and accelerate, and in principle you can even get supersonic flow. And this was main problem when we didn't see it. So we assumed that even at the presentation of the PSI, we realized that, okay, we should have a region when we have a subsonic and a region when we have very strong negative currents, supersonic flows. But this was not the case, as I will say. So in order to see this, okay, this was very nice, maybe simulations, but you never trust fully only simulation. You have to have corresponding analytic model. And after a number of attempts, we managed to do it. So we realized that if we start for particle and momentum conservation equations and neglect, let's say, small terms like temperature gradient versus electron gradient, neglect ionization because plasma usually is very cold in this area, neglect viscosity, we get these equations. We consider one-dimensional electric field, just normal to the wall component. And we, as we know, we cannot request the sheath entrance to be fixed as a point where Mach number equal 1. So we need another physics another point to say that we have here start of the magnetic sheath or plasma sheath. And this point is naturally to assume that this is the nearest to the wall point where ions are still magnetized. So this is mathematically is given here, and from these equations and this condition of the some transformations, we end up with following conditions of the Mach number near the sheath entrance. This depends on parameter kappa, depending on the frequencies of momentum transfer frequency between neutrals and ions, and also electron-ion friction force and current. Now, if we see, it's a proper expression from the point of view that if you go, the collisionality goes 0, we recover classical value Mach number equal 1. On the other hand, if we have some friction, it never will, Mach number will never reach 1, as we see from the simulations. So in our case, in this equation really confirms what we see in the experiments. And the next step also here was we see that it should depend also on the current. And the main problem arises when we started to make simulations with current. But before doing this, let me see that if we have current-less regime, simulations perfectly confirm this equation. So if we take a simulations no current, so floating sheath, we get a quite reasonable agreement with the between peak and analytic simulations. And even if we make simulation the whole sol, we get quite good agreement with the this model. So it means that if we consider full sol, including all physics, still this equation is recovered very well. Here, constancy means that this parameter does not depend on sol, so it's the best way that showing that exactly at this point when it starts to change exactly this distance from the wall, we can assume that this is sheath edge. And as I promised, I show now expressions when we have current. We should have some current regime, but we do not see it. So we increased what we did. We just increased biasing of the sheath. And we increased enormously much because when we have a temperature of electrons 1, and we increase 50 volt biasing, which means is normalized biasing is 50, which is enormous number, if you know from the prop theory, and we see a very small change of current and very small change of, very small change of Mach number. And it was strange because based on this expression, which was given previously, it should be quite dependent on the current in such a high current regimes. The question was why? And this we obtained answer to this after analyzing of distribution functions of the particles at the sheath entrance to analyze what is the friction between electron and ions. So the classical model of friction says that you have an average velocity of ions and average electrons, and there is some difference. This creates a friction. If you look to the distribution function of ions at the wall for different current regimes, comparing with Maxwellian, it's quite near to Maxwellian here. Once more, here we do not consider impurity, and so these distributions can be much more different if you have impurities. We see that really it's a kind of shifted Maxwellian for ions, which is used in many analytic models. So this is our velocity for ions. But the problem is the current of electrons is not made by shift of electron distribution, it's made by cutoff. So it means that if you consider current of electrons at the sheath entrance, this is a low density case, so it's a green one, showing really classical cutoff. So these are electrons are coming to the wall and due to the, and they are absorbed, and so fast electrons are absent in the outcoming from the wall direction. And with increasing density, it's of course this effect decreases, but you still have, you can see this difference between these points. But in any way, you have no shift in the direction of the wall. It can't be also physically happening because electric field is directed opposite direction. It means that actually there is all times only one component here. There is no average velocity in the meaning of classical models or fluid model. We have to neglect this, and it means that electron-ion friction is dependent practically on the ion velocity at the sheath entrance. And this is independent, of course, and if you multiply with And this is very small value, is independent of electron current, and you will never get contribution to the electron total current here. It means that in principle we can neglect contribution of current in the condition, boundary condition of the sheath. Okay, this is now our expression of the sheath where we neglected the contribution of the current. And what are the consequences? The first consequence is if there are two possibilities. Possibility A, we consider just fixed density and temperature, and we see what will happen if you have a fixed density and temperature with fluxes, and of course these fluxes will reduce. So this is, for instance, heat flux to the divertor plate when we have a constant density and temperature. This would be, of course, ideal, but unfortunately, density and temperature is definitely not constant. So we consider another limiting case when we have a constant flux, and then what will happen with density? So if we have a constant flux, so assuming constant temperature, then we have that with increasing of collisionality, we are increasing density here. Important to note, either in both cases, constant density or constant flux, we do not have any significant change of potential drop. So it means that for probe theory, you still can easily use probe models, probe models even for very high collisional plasma sheaths. On the other hand, these are two limiting cases. So in reality, probably density that will change as well as friction, but these are giving kind of limiting cases which we consider. And in order to see, the first attempts were made to implement this new model in the SOAPS ITER code. It's a fluid code. It's probably a major code which is used in Diffusion community for modeling of plasma transport. It's gray code here. It's a standard ITER code. And this model was implemented, and we considered that relatively, let's say, a weak case when we have Mach number equals 0.6. And this is comparison between classical model, assuming Mach number equals 1, and second model, it's a new model with 0.6. But as you can see, velocity, as was expected, is changing, and also density is changing. So we obtain case when flux, total flux, plasma flux is constant, increase density, increase velocity, and also decrease velocity and increase density. And so you can see that there was no, as I say, there are no changes in particle flux, but increased density in divertor and UX point actually. What this means, I'm coming to my summary. This means that we have a new model of density or high density plasma sheaths, collisional sheaths. It is mainly will form in next generation machines in front of diverters of next generation machines, and it will be characterized by subsonic plasma flows. This will have a number of consequences, because if you have a different density or different parameters, hidden seat loss, definitely the PSI plasma surface interaction process will be affected. A new definition of magnetic sheath intervals is proposed. It's not a point where Mach number equals 1, which usually assumed. There is no Mach number equals 1 point, but it's a nearest point to the wall surface where plasma is still magnetized. It has a number of advantages because it's more general, it reduces to classical definition, and it's really its border of replication of fluid codes, because fluid codes cannot enter area where even gyrokinetic codes cannot enter area where plasma is not magnetized anymore. So it means that you need boundary condition exactly at that point. Good that this new model, I mean, this Mach number at the sheath centers depends on ion neutral collisionality and reduces to the Bonko-Dura condition in collisionless case. Of course, this means that it's lost universality, so it depends on collisionality. So whenever you want to obtain the condition, you have to know what is the collisionality at the region. So it's more complex to derive this expression for concrete cases. As I already said, this new model predicts a significant increase of divert plasma density and or reduction of plasma and flux into the divertor plates. And I want to say that majority of the simulations we have performed under JFRS project, HD sheaths, and I want really to thank the IFERC team for their support, because it was perfect simulation, and that whenever I needed some So I had some questions, reaction was immediate. I want to say that from the simulation point of view, this project is closed. So we do not continue, at least under IFERC, to continue the simulations. Unfortunately, paper is still pending because we switched to new simulations that they require much more time than we expected. Anyway, thank you very much. And I'm ready to answer your questions if you have them.
Okay, thank you very much. Now the question and comment, please. No questions? Okay, please.
Hello. Thank you very much. Can I ask?
Sure.
Thank you. So yeah, I would like. Yeah, usually we use a calculation of the fluid code in the plasma transport, and so my question, and also the demo calculation case. I think it's as you know, the density is increases to 10/24 or more. So we are interested in it in that situations. We are interested in it energy transport to the target. So if your case, your simulation case, such as Mach number is lower than 1, so I'm a little bit wondering how do we extrapolate or incorporate such a effect? So, maybe our work, maybe we can modify the shear transmission factor or any other parameters. So do you have any suggestion to include your prediction to the heat load estimation by fluid code?
Yeah, I mean, thank you for your question. Yeah, I mean, one has to, I mean, there are 2 points. First of all, one has to say that your gamma does not change, actually. Probably you mean CSC transmission factor, because if you consider the heat flux is proportional gamma times plasma flux. So it means that this correction is needed for plasma flux, but not for the CSC transmission factor. So whenever you have a proper plasma flux, of course, you can use the classical expression for the heat load, which is CSC transmission factor times plasma flux, plasma times electron temperature. On the other hand, as I already showed, you can implement this condition, which was done successfully in SOAP-CETA code. So I mean, there was no interest in studying precisely the plasma surface interactions, but we don't know. So can we neglect this for this case because plasma density increased by 40%? So does it really change something or not? For demo, situation is different because what I said up to now, it just, let's say, applicable for eta and let's say moderate densities for demo. The problem is that in case of demo, you cannot neglect some effects which are essential, like opacity. So you can, because the radiation loads and also radiation effects on the plasma is very important. Opacity is quite high. And thus we are planning and we are doing this under, say, the TSVV7 project, this European theory simulation, validation and verification project. And this
excuse me.
Yes.
Opacity means photon absorption or other.
Yes.
Okay.
Yes.
Okay.
Because these models usually assume that you have some radiator collisional model and you are implementing some, let's say, rate coefficients based on this model, and you neglect other effects of these photons. In very high density plasmas, this cannot be done. And once more, for the densities you consider, and come to these plots, if you have a densities above 10 to 22, and you have correspondingly temperatures of the order of 1 eV, so you cannot use plasma equations at all. Plasma is not classical anymore, so it's quantum mechanical. So that is.
Yeah, our case is just over the 21st, so it's not too high. But if the more power exhaust demo, such as a 3 gigawatt or more, so this case will be reach such a level, I think. Okay.
Yeah, as I said, we collaborate with demo team and also with SOAP simulator who are doing demo simulations, and it's up to them. So if they want to implement and use this model, we are open to provide any data. So it's quite simple. It's not so difficult to implement.
Okay, thank you so much. So if we have a time to meet, it's very better to or discuss, or maybe the next time of the BA discussion of the diverter. So thank you.
Thank you very much.
Okay. Any other questions? No? If not, thank you very much. Okay, we shall move the third speakers. So Dr. Yanchenko, Kinetic simulation of turbulence in JT6 CSA with gene code. So please start. I can't hear your voice. No. Sound problem. We can't hear your voice. Yeah, sound problem. Some problem of your microphone. No. No, your voice.これなんかテストできるんだったっけ？サウンドの。
自分ではできるそうです。そうですね、自分では。今この場でだって。
No sound, no sound. So there might be some problem on your microphone, I guess. チャットちょっと見てください。何かチャットの方でなんか打ってみてくれへん？なんかヘルプを。
I think it may be possible to switch.
Okay, so maybe you can check to your microphone. So change to the program. So maybe Asakura-san first.
Okay, sorry, I'll check. I think, wait a second. Sorry, it's I tried to and do you see?
Okay,
yes.
We can see.
Okay, so I should go back. Sorry, I did not prepare. Okay.
Okay, so
okay?
please start.
Okay, okay. I would like to start. And sorry. I think I'd like to talk the progress of sonic simulation for diverter detachment in EU demo, and also the helium exhaust in JA demo. This is a report from the project SS demo. I think it's the first topics. I do not have a good introduction, but the first talk is related to the benchmark of the sonic and the source eaters. We, in the phase 2, DDA phase 2, we started the benchmark of the sonic and the source in both for EU and the JA demo. So that this is the first step of this benchmark work. Because the EU demo is a lower power exhaust comparing to the Japanese demo. So this is, we started. So this is the first part is a presentation. And recently we are progressing. And the second is a helium exhaust study by Sonic for JA demo diverter. This is the previous, and these 2 years we spend computer resource for these simulations. So this is a particle exhaust and optimization of the diverter, demo diverter design. At the same time, we'd like to acknowledge JFRS 1 because we use for the key exhaust parameter surveys such as density and also diffusion coefficient, and also model development for the sonic. And so, recent last year's publication is the following. But anyway, the first I'd like to introduce sonic shortly. The sonic is like SORPS code, so that this is an integrated diverter code. The plasma calculation is a fluid code, and also neutral, and also impurity is a Monte Carlo kinetic code. So recent development of the sonic is modeling framework using the MPMD approach, and also MPI data exchange schema has been developed. So the first that we can use for the mulch impurity calculations. At the same time, and we can just computer arrange for the node of the computers for efficiently. So sorry, and maybe it's other work. The modeling development is as following. I don't explain here. So that's for the first topics. The sonic simulation for EU diverter is started from last year. The sonic SORPS mesh has been successfully converted to the SORPS either to the sonic format. The mesh is size is like here. So this is the original sonic SORPS mesh for the EU demo. And in this case, they do not have a liner structures here. Recently, we converted this equilibriums and the first world data to the sonic simulations. So this is sonic simulation, almost similar to the EU demo. This case is also shielding liner is installed, and also Monte Carlo simulation mesh is also shown in this figures. And also the argon is a shielding impurity, is a path from the outer diverter, and the deuterium is path from the midplanes. So also we injected in this mesh, we exhausted power from the core edge boundary in the EU demo case, 160 megawatt, and also exhaust particle is 5 times 1022 deuterium per second. So in these situations, we scan the radiation power in the edge and also source and diverters. So this case is in sonic case, we shaded we shaded the argons, and also we fixed the given values, these three. And one case, for example, in the one case, we use this case and we feedback the argon shading rate, and then conversion solution of this total this radiation power is obtained, and then this we call the solution for this radiation total radiation powers. So this corresponding to the fraction of the exhausted power in the 60%, 70%, and 80% corresponding. Deuterium gas buff is given values. One of the big, this is I mentioned. So the pumping is also the settings in the constant so far. At the same time, the puffing, deuterium gas buff is we change from 4.8 to 6.6, 9.6. This value is similar to the JA demo gas buffing. But on the other hand, in the EU demo SORP simulations, this value is about 3 or 4 times larger than the Japanese gas buffing. But so far we are buffing this one. But in future, we will increase the gas buff to these values. One of the important thing is the diffusion coefficient. In SORP's calculations, in the edge regions, the diffusion coefficient for the energy and also particle is about 0.2 times 0.2 square meter per second, and so is diffusion for the power is 0.19, and also deuterium. Sorry, and the diffusion for a particle is 0.41. So to simulate this kind of values, we fix a constant and the 0.2 for particle and energy. And in case of the solar regions, we fix these values. Unfortunately, in the sonic, we cannot change the diffusion coefficient in the edge regions. So such a kind of profiles. So we use a constant value for this one. The other parameter is the same of the for the SORP's calculations. The first result is lower radiation case. This case is a 70% radiation of the P out, PSEP. So this case is we change the gas buff from here to here. Right figure shows that it's a lower gas buff case. So in this case, in the you can see this is the outer diverter target, and the temperature is quickly increased, so that we can see the very detachment is mostly almost detached region, detached in the separatrix, and quickly the temperature increases to the attachment, and the temperature profile is like here. Sorry. So in this case is a peak heat load is very high because the temperatures increases. So the plasma transport component is 70 megawatt per square meter, and the total increases the radiation, and the surface recombination is 21 megawatt per square meters. So radiation is very locally like here. So on the other hand, if we increase the gas buff, deuterium gas buff, to the here. So the detachment a little bit is extended, but and at the same time, the separatrix is detachment is almost appears. So therefore, in the heat flux is also reduced. The total heat flux is 12 megawatt per square meter like here. So, but still the detachment region is very narrow for the case of the 70% radiation case. The next case is 80% radiation case. So the typical case, in this case is argon fueling rate is also, argon seeding rate is also increases like here, and the 4 times high use. So this case, on the other hand, is because it's soil density at the midplane is reduced. Therefore, we need more argon gas bath to obtain the 80% radiations. So inner diverter is a fully detached right here, and the outer diverter radiation is increases on the leg, and the detachment region is also increases about 8 centimeters. So the peak heat load temperature is also gradually increases. Therefore, in a peak, and the heat load is reduced to less than 4 megawatt per square meter, like here. So in this simulation, in case of the low diffusion coefficient case, the temperature profile is very sensitive. Therefore, on the peak heat load is changed from quickly to the reduced right here. So this is sorry, it's too much. Okay, sorry. This is a case. Sorry. Oh, sorry. It's sorry. I changed. So this case is a 80% case is a low diffusion case here. So it's about 4.5 megawatt per square meter. So this is the same. So this slide shows that it's larger diffusion case. This is about similar to the ITER simulations, and also Japanese demo case. We use this one. This example shows that it's 70% radiations, and also this case is 80% radiations case. So this case is in case of the higher diffusion coefficient case. You can see that its temperature increases. It's more gradual, and the detachment is even the 70% radiations. Detachment is extended 5 centimeters. Therefore, in the peak heat load is about 5 megawatt per square meters, including the surface recombination and the radiation and the neutral load, like here. So in case of the 80% case, as I mentioned in the previous, in the detachment region is extended and the temperature is reduced. Therefore, in the attachment case, therefore attached regions, therefore the peak heat load is reduced, but the reduction is more gradual comparing to the European slopes diffusion case, small diffusion case. So this is a example of the different. I would like to just explain the effect of the diffusion coefficient on the upstream plasma profiles. So you can see that in case of the lower diffusion coefficient case, and this is a diffusion coefficient I mentioned for Japanese and also ITER case, ITER used. So this case is in this case is a more higher gradient. Therefore, the temperature is higher comparing to the light case. At the same time, it's on the other hand is density is reduced right here comparing to the gradient is large, but the temperature gradient is increases, but the separatrix temperature density is smaller, like here. So next one is e-folding heat load profiles. So heat load profiles is you can see the mostly dominant, the electron heat flux is dominant in near the separatrix. And so it's the E-folding, decay length, the typical decay length is about 1.5 millimeters. And this is quite similar to the total heat flux and also electron heat flux. One of the interesting things is the ion component. The ion component is, this is a peak, but this is a shorter, this appears here. And this is a higher, a larger diffusion coefficient case. And at the same time, the electron heat flux is dominant in the near the separatrix. So, and also shorter is appears in ion heat flux like here. So in the first order regions, both cases is ion heat flux is dominant comparing to the electron heat flux like here. So that is one of so this kind of value is both smaller than the eta simulation case, such as Kukushkin's papers. So the explanation of the why it's such ion. So you can see that it's due to such a kind of ion heat flux, the total heat flux profile is have a shorter of like here. So why this kind of things happens? The ion heat flux is ion heat flux component is convection conduction. If you in the outer target, due to the high recycling regions here and near the target, therefore it's flow reversal appears in the simulations. Usually the flow is going to the diverter. On the other hand, especially locally, the recycling is enhanced. Therefore, the pressure is increases. And the flow reversal appears like here. This flow reversal is the flow reversal is more dominant. So, flow reversal. Sorry, I think it's this is a right hand side and left hand side is reversed comparing the previous view graphs. I'm sorry. So it's in this case is a more larger diffusion coefficient. So the flow reversal is more wider. Therefore, in the here in the shoulder is more larger, like here appears for this case. So the detachment region is more wider. At the same time, this kind of a flow reversal is transported to the impurity to the upstream. Therefore, in the problem is the partial detachment appears. Most maybe due to one of the reasons. But it is noted that in the experiment, we don't have any measurement. We don't see such a flow reversal from these locations. So therefore, this may be one of the question for modeling comparing to the experiment. So that is I should note it here. So it's I will summarize this kind of a work in this. So it's sonic simulation studied for EU demos for benchmark. So the calculation situation is we can scan the density, we can scan the radiation powers, and for the original EU SORPS case and also the Japanese diffusion case. So you can see that in the case of the lower diffusion coefficient case, the detachment, peak heat load is reduced so quickly. And it is also sensitive to the deuterium gas bath case, this amount. So the detachment is very narrow and very sensitive to the temperatures. And the case of the 80% radiation case, the plasma load was significantly reduced. And on the larger diffusion case, the radiation, so the peak heat load is gradually reduced. Finally, these regions in the 80%, these are comparable because the peak appears in the detachment regions, low temperature regions. So, and also we can see that it's a flow reversal in the simulations. Therefore, in the heat load, the peak heat load profile, and the peak heat flux profile is quite have a shoulders in the far scope of radius. So that is the situation. So the distributions upstream soil plasma and the impurity will be compared. Impurity such transport, such as the thermal and the friction force, will be compared for the sonic. Will be compared in futures in this years, I think. So on the other hand, in the slope situations demo, right now they are working to work. One is installing the shielding liners, neutron shielding liners in the dome regions. So at the same time, it's they change the equilibrium data to the new one, higher toroidal field. Therefore, expansion is increases. So that will be affect detachment situation. Therefore, in the maybe we can compare this data to their previous data without dome. Then we will together calculate a similar shielding liners in futures. So that is one topics. I think is how the time? A little bit. Do we have a time?
Yeah, maybe sometimes 1-2 minutes.
Okay. So I quickly through the helium exhaust result. I think it's this is one topic is a particle and helium exhaust study for Japan and for Sonic for a Japanese demo and SORPS for European demo. Because one topic, this is interesting thing. We are focusing the how do we design the dome, and so as you know, the shielding line is very simple, like here, so and a very low height. Therefore, it's is this related in the Kukushkin's previous ITER work in the he suggested it's a dome height. Dome is necessary to exhaust its helium. The compression is enhanced in the diverter. So therefore, in the we are designed. We are interested in how the dome affects exhaust, particle exhaust, and helium exhaust. So anyway, it's that is motivations. So in the case of the Japanese demo, exhaust power is higher. The 250 megawatt is exhausted, comparing 100 megawatt higher than Europe. And here, the particle is exhausted, and also helium exhausted here. So finally, it's the partial detachment is observed in outer diverter. The inner diverter is a full detachment. So if we change the gas path like here, the heat load is reduced here. Peak heat load is reduced. Density is increases. The helium exhaust, the helium green show the helium concentration in the edge. That is a little bit reduced, but the level is 4 to 7% in the edge. So that this is there is no problem for the there is accumulation of the helium is not observed. And the next diffusion coefficient is one of the important, especially in the edge regions. So the European pointed out their simulation the diffusion coefficient is smaller, I mentioned before. So this case is a helium concentration in the edge is about 20%, but this is not normalized by electron ions. So this is 20%. That is higher than the design values. So therefore, we reduce diffusion coefficient to the half values, like here. This case is we can see is a little bit increased, but on the other hand, but this is still acceptable level of the demo designs. So that is our situation. The future we will reduce diffusion coefficient. The sensitivity is we will study. Then we can change the dome designs. Then we can see the exhaust studies. So that is our this year's work. So I think this is a summary of the helium exhaust. And also the future work is more future work. The benchmark with EU and the Japanese demo. That is one of the tasks of the BADDA. And also other things is integration transport code, the sonic and SORPs topics. That this is the main plasma transport is one of the our task for not the BA, it's a Japanese demo designs. And also renewing the door to incorporate the drift is one of the long-term work development of the sonic. So thank you for attention.
Thank you very much. Okay, so now the question, please.
May I ask a question?
Yeah, please.
Yes, thank you.
Hello, Asagura-san. I have two questions, if I may. Thank you for your presentation. The first question is, for demo, one expects, at least from the kinetic simulation, what we see, that significant fraction of heat load is done due to charge exchange neutrals. And my second question, if you go to, for instance, previous slide is 7 or 8, the parameters at the sheath entrance are exactly what I was describing. So, and sonic, as I know, is using a classical boundary condition. So, in your opinion, how your results will be influenced if you put for these parameters what we see in the kinetic simulation, Mach number equals 0.2. So these are two of my questions. Thank you.
Okay. First question for charge exchange. And as you mentioned, it's in case of the attached or regions, you can see that it's neutral. We can calculate the neutral load, but this case is very small, so there is no problem to evaluation because the plasma transport component is more dominant. So in case of the detachment case, this is a surface recombination because it's not a charge exchange. So mostly the charge exchange is included in the neutral load. This is a volume recombination part is also. So therefore, in the influence of the neutrals load is like here. So this is one of the questions, but it's not major. So next, the second question of your information. So one of the problem of we are wondering because it's so as you mentioned, maybe you can see that it's in the detachment regions, and for sonic simulations, the temperature is reduced to about 1 electron volt or less than 2. So it's still the ionization is occurred. Therefore, it's a recombination is not volume recombination is not too large. Therefore, in the we can see the surface recombination is large. Even the plasma transport is reduced. Therefore, it's one of the question for us is this surface, how much we can transport this surface recombinations part to the target. We counted 13 electron volt for each surface recombination. Therefore, this value is increased because the density is such a high. So that one thing. So as for the neutrals, so right now it's Hoshino-san's group. He's a kind of a developer of the Sonic. His group is evaluating how much the new charge exchange is influenced in the diverter, especially near the target regions, from the more upstream regions. So that we can discuss this kind of a situation right now, including him. So that is my simple answer. So is that okay? Or do you have any more question about this kind of result?
No, thank you. I mean, just my point was just to put despite 102 to see how it changed. Just boundary condition. I think Sonic has this input parameter, I guess, to see how it's because it's not just only Mach number. It's that area. Whenever if you calculate charge exchange collisions, you find out that plasma is not magnetized at all. So it means you have to put boundary condition a little bit up. But it's a separate discussion. I propose if you wish, we can continue because we collaborate with European team of demos, including, for instance, Fabio Suba, and we can discuss it.
Yeah.
Thank you.
Svein and Suba-san, we have a time discussion in 3 months, every 3 months or something, 4 months. So you can join this work, these meetings.
Oh, thank you very much.
Yeah, I will note. Thank you.
Thank you.
Okay, any other questions? No? Okay. Thank you very much.
Okay, thank you.
Okay, so now we shall take a virtual group photo, then continue to the presentation. Okay, so please turn on your camera, please. Our staff will take photo. So everybody, please turn on your camera. Okay, so
thank you for now I take quickly 5 pictures. So please keep your smile.
Not yet.
3, 2, 1. Okay. Please just wait a more second. Yes, okay, thank you very much.
Thank you.
okay, so just finish to the virtual photo. So we shall continue. So Dr. Yanchenko?
Yes, can you hear me now?
Now we can hear you.
Okay, excellent. I changed computer, but it's good. Okay, so I can share my screen.
Sure, please.
Do you see my screen?
Yes.
Yeah, okay.
Okay, so I can start. So hello everyone, my name is Elwin Yanchenko, and I will present you this work we have been doing on gyrokinetic modeling of turbulence for JT6TSA. And before I begin, I would like to acknowledge everyone who has participated in this project, in particular Moritz Puchel, who has helped us a lot to analyze and interpret our results. Also, I would like to thank the JFRS 1 team for the support and made the simulations for this project possible. So the JT6TSA is currently, thanks to its large size and high magnetic field, is one of the most suitable reactors to study ITER, demo, and reactor-relevant regimes. And this includes studying the effect of microinstabilities that leads to anomalous transport that is greatly limiting the reactor performance. So in this project, the goal is to try and predict what will the turbulence be in GT6TSA. So we don't not have yet experiments to work from, but we use predictive input parameters to our simulations and try to have a look at what the turbulence will look like. And originally, this project, it started as a part of a feasibility study for a turbulence diagnostic that is planned for GT6TSA. And this is the tangential phase contrast imaging diagnostic that will measure electron density fluctuations. So this presentation is organized now as follows. To begin with, I will present you the details of the scenario that we're looking at, the GT6TSA scenario. Then we'll have a look at our gyrokinetic simulations, so the code we're using, the parameters and the simulations conditions. Then we're going to have a look at the linear results first that show us what type of modes and growth rates we have. Before going on to the nonlinear study, we will look at the saturated states and the heat fluxes and the transport. And then finally, I will make a summary and take the conclusions. The scenario we're looking at is the so-called scenario 1. It's one of the predicted GT6TSA discharges that were predicted using reduced transport modeling. So we have profiles and input parameters that were computed with a set of codes. So here, topics, Acome, and Tosca. And this discharge is characterized by a double null equilibrium, as you can see here on the left, as well as a large value of beta, which is the normalized kinetic to plasma pressure. It also has a large amount of heat. So we have 34 megawatts of MBH and 7 megawatts of ECH, exactly. So 41 megawatts in total. Now, in our case, we won't do simulations for the whole plasma, but we will focus just at one radial position. And this is indicated by this green flux surface on the left. So we're going to do simulations near to this radial location, as well as indicated by the dashed line here on the right. So the beta that we're considering is about 2.7%. The code we're using for our simulations is the gene code that solves the gyrokinetic equations and allows us to predict and have a look at what the turbulence is like. It's possible to do both linear simulations and nonlinear simulations, and the simulations can be both gradient-driven or flux-driven. In this case, we use the gradient-driven flux tube model of gene. And the flux tube model means that we're doing the simulations next to a field line at close to one radial position. In gene, we use an efficient coordinate system that makes use of the anisotropic structure of the turbulence. And as input parameters, we give experimental equilibrium, which in this case is a predicted experimental MHD equilibrium. Then we give the species information, so this includes temperature, densities, charges, and mass to specify each species we are simulating. Then we can include collisional and electromagnetic effects. Now, in our case, we have done the following. So as I mentioned, we're looking just at one radial position. Right now, this is close to mid-radius, so this rho is 0.6. Then in general, we're going to consider 4 kinetic species. So we have kinetic electrons and main deuterium ions. Then we have the carbon impurities. And finally, due to the presence of MBH, we also have the fast deuterium ions. And in this work, they are modeled rather simplistically. We simply take a Maxwellian, but at a larger temperature. So the fast ions have a higher temperature compared to the bulk, but are otherwise modeled by a Maxwellian. We're going to include collisions, even though they have quite a small effect in our case. But most importantly, we will include the actual value of beta. So we will consider electromagnetic fluctuations, and we will include compressional magnetic field fluctuations, so including this delta B parallel. And this is going to be done consistently with including the grad B and the curvature drifts of the guiding center of the kinetic species. We will not consider ETG scales here, even though we have ETG modes, because their multi-scale interactions between ion and electron scales is predicted to be quite small, as can be computed through this ratio here. So here we take the growth rate and compare it to the wave number at ion and electron scales. And if it's larger, then we can assume that the multi-scale interactions should be small. So in general, in our simulations, we will just focus at what happens at the ion scales. Now, more in detail, the exact input parameters we're going to use are as follows. And what really stands out is the fact, as I mentioned, we have 4 kinetic species here. So we have the ions and carbon. Then we have the fast deuterium ions coming from MBH. And these are modeled with the Maxwellian at a higher temperature. So here we have about 10 times the electron temperature. Then another thing which is important is the fact that we have a large beta, which is here, as you see, 2.7%. So we have now introduced the scenario we're looking at, and I will move on now to our simulation results. First of all, we're going to look at the linear study to have a look at what kind of modes we have and what parameters seem to be important to include before going on to the nonlinear study. So for the linear study, what we do is that we evaluate the growth rates and frequencies of the most unstable modes. So you can see these two are plotted on the left here. So we have the growth rate on the top and the real frequency of the modes on the bottom here. First, we take beta equals 0, meaning that this is an electrostatic simulation. And we consider, to begin with, only two species. So we have deuterium and kinetic electrons. This gives us then the blue line here. You can see behind this green line. And if we look at the frequencies, we have a slight positive component here, meaning that the modes are of ETG type, before transiting to negative frequencies, which means that these are TM, or at larger scales, we have ETG type modes. Now, if we add impurities now, so we go from blue to the red line, we can see that we have a stabilization, so a reduction of the growth rate here when going from blue to red, which means that impurities are stabilizing. The green line here keeps the effect of impurities in the collision operator, but does not otherwise include them as a species. And as you can see, the effect of the collision operator is actually quite small, but the main effect when adding impurities comes from diluting the main species. If we go one step further and we include also fast ions, we see that we get just a very slight increase in the growth rate at the ion scales and a slightly larger increase at the electron scales, but otherwise there's no big difference. The next step is to repeat these scans, but including beta. Then we get some changes, as you can see. First of all, we can see that all growth rates have slightly decreased. So we have stabilization because of beta. In particular, there's a big effect for impurities at ETG scales, but otherwise, all the other cases have just slightly gone down. What's interesting, though, is if we look at the real frequencies, you can see here that we have a new set of modes if we compare with the corresponding electrostatic case. First of all, if you look at fast ions, we have a high frequency mode that appears at very low wave numbers. And then we're going to come back to this later, as this actually is going to cause us various complications in the nonlinear simulations later. We still have an ETG scale sort of in the middle, and then a TM/ETG scale coming up here at larger QIs. Now, this is still without compression magnetic field fluctuations. If we also include that, we get to this final result here shown on the right. And what you can see is that the impurities, the biggest difference is in fact for impurities. So at ETG scales, we don't have this low growth rates, but they become much larger. And in fact, if you look at the other cases, there's a slight destabilization due to these delta P parallel fluctuations, both for fast ions and if we only have the two species. We also have a slight, again, change in the frequencies. Now, the conclusion from this is that essentially we need to include really all four species. We need to include beta, and we need to include delta B parallel to properly model this scenario. Potentially also because the effects we see here might be enhanced nonlinearly. Now, in order to understand a bit better what is the role of beta in the simulations, we have done separate scans where we varied the electron beta. Again, we compute the growth rates here on the left, the real frequencies in the middle, and then on the right, we compute the ratios between the electromagnetic and the total heat flux. Now, these are exponentially growing, but it's still possible to compute the ratios in order to understand what type of modes we actually have. Now, what we see here is that if we start at low value of beta and we increase it, we get a decrease of the growth rates and a sudden increase. This decrease essentially is where we have the KBM limits. The dashed black line that you have here is the beta we're using in our simulations, which tells us that all our cases are under the KBM limit. We distinguish between different cases. First of all, we have the blue one, which is, again, just two species without magnetic field, parallel magnetic field fluctuations. If we add those, we see that we have slight destabilization as we increase beta. So this in fact is very small at slow beta, but this destabilization increases as we increase beta. If we consider impurities, then we go from the green to the red line. So we have a stabilization at all beta because of impurities. Finally, if we add fast ions, we have almost no effect at very low beta, but this effect seems to be slightly increasing with large beta. There is some kind of enhanced stabilization or destabilization in some cases of fast ions when you have a larger beta. if we look at the ratios for the heat fluxes, you can see that essentially we have electrostatic modes at low beta. Then exactly at the transition from this mode we have in the beginning to the KBM mode, we get some electromagnetic components before transiting to the electrostatic KBM mode. So this again illustrates that we really have a vast range of modes that are present in our scenario, and that's going to affect our nonlinear results. Now, this was the linear study. We have sort of understood a bit what kind of effects we need to include, and now we move on to the nonlinear study. And the very first thing we do is that we take the nominal parameters that were predicted by the reduced transport models, and we compute the heat fluxes. And what we find is that the heat fluxes are in fact very, very small. So what we expect is to get a heat flux that is comparable to the injected power. So it should be 41 megawatts. But what we see, so here I show the time trace of the heat flux for the electrons and ions. And what we see is the fact that this heat flux becomes very small and much lower compared to what we expect. So it's clear that we somehow have to change the input parameters. And here we do this by increasing the gradients. So we increase the gradients in order to try and increase the heat fluxes and come closer to the value that we actually want. However, if we increase the gradients, we get another issue, which is a runaway instead in the heat flux. So keeping nominal value of beta, simply increasing the gradients, and here I mean increasing by more than 10% from the nominal value. What we find is that the heat fluxes, in fact, do not saturate. So they just become very, very big. And this is, in fact, due to the non-zonal transition. And in order to quantify or verify that this runaway is, in fact, due to non-zonal transition, we have used a diagnostic that has been developed to check exactly this. And it works in the following way. What you do is you take a field line and you follow its 1/2 poloidal turn, and you look at how much is it radially displaced. Now, normally, a field line is going to be slightly radially displaced after 1/2 poloidal turn, but then it's going to come back after the second half. However, if this radial displacement is larger than the correlation length of the radial magnetic field, the field line is going to decorrelate and it's not going to come back on itself, meaning that you will have a breaking of flux surfaces. And when you have this effect, you can potentially weaken or suppress the zonal modes, leading to this non-saturation of the heat fluxes, because the zonal modes can no longer saturate your heat fluxes. An important thing to know is that this radial displacement of the field scales with beta. So if you have a larger beta, you can also have a larger increase in this radial displacement, thus a larger risk of obtaining density. It also has, also the temperature gradients or the profile gradients also have a role on the length of this radial displacement compared to the radial correlation length. Now, in order to illustrate this, if we first take a case without an NZT, we see the following. So here on the left, you have the correlation function, and the black dashed line indicate the radial correlation length. So you can see here it's about 8.6 in terms of ion gyro radius. On the right here, we have the radial displacement. And what you can see is that, in fact, the radial displacement of the field line after 1/2 poloidal turn is quite small compared to the correlation length. So in this case, the field line stays correlated, and it comes back to itself, and thus we have no NZT. Instead, in our case, for the runaway I was showing you before, we have this. So you can see the correlation length has slightly increased, but we have an even more increase in this radial displacement of magnetic field lines, which means that the field line is going to decorrelate, causing breaking of the flux surface, which leads to an NZT. Now, in order to characterize what is the KBM threshold, we have been varying the value of beta and the temperature gradients of electrons and ions. And what we find is this blue line here. And essentially what this means is that anything above the blue line leads to an NZT, whereas if we take below the blue line, we do not have an NZT. The dashed black line indicates the nominal value of beta. So you can see here already for about 10% increase of the gradients, you're going to hit the non-zonal transition and you won't be able to simulate. So in order to be able to increase the gradients, which we have to do here to rise the heat flux, we need to compensate by lowering beta. So this is what we did. And this made it possible to now increase the gradients and get a larger heat flux. Now, so far, all these results I've shown you have been only for 2 species. as I showed you in the linear simulations, we also have to include impurities and most importantly, fast ions. However, if we include fast ions, we get yet another feature, which is this very strong oscillation. So here again, I'm showing the time trace of the heat flux. Here is for the main ions in blue and the fast ions in green. As you can see, when we include fast ions, we get a very strong oscillation and also a suppression of the heat flux coming from the main species. Instead, most of the heat flux is in fact coming from the fast species, as you can see here. Now, if we look at the frequency spectrum, we can see that this indeed comes from a very low Ky mode. So if you look at this Fourier transform here of the electrostatic potential, you see a very large frequency component here. And this frequency, in fact, corresponds to this oscillation we see in the nonlinear simulation. And using linear simulations, we have been able to characterize this mode and understand what parameters it is sensitive to. So here I'm showing the frequency of the most unstable mode when we vary the fast ion temperature or the fast ion temperature gradients. The nominal cases are the ones that are shown with the dashed grid line here. You can see leads to a very high frequency component. However, if we very slightly change the fast ion parameters, for example, we go from the nominal 10 times the electron temperature to 9, we already make this mode subdominant. Similarly, we could also change the fast ion temperature gradients. So what this shows is that this mode seems to be very sensitive to the fast ion parameters. Now, interestingly, in the linear simulations, we only notice it for Ky around 0.5 here, whereas in the nonlinear simulations, we see that at a much larger value of Ky. And this still remains an issue. We don't really fully understand what is happening. One idea we had is that it could potentially be triggered by the non-linear variations of the profile gradients. However, we saw that this was not the case. So this is still like a question we try to answer, why this really appears in the nonlinear simulations at larger Ky. However, through these linear results, we then try to change our nonlinear parameters or simulations parameters in nonlinear simulations, and we see that just as linearly, we can destabilize this high frequency mode. So what I just show here is again the time trace of the heat flux for main ions and the fast ions. We start off with the nominal parameters giving this very high oscillation. However, if we slightly lower the fast ion temperature, so from 10 to 9, we get rid of this oscillation and get something that we can actually simulate. Now we believe that, okay, we found a case that is reasonably close to the heat flux that we want. And the next step would be to carry out a convergence study for this. However, it turns out that even though we are at a larger heat flux, we are still very close to the critical gradients, making it very complicated to carry out our resolution studies. In order to understand where is the nonlinear critical gradient for this case, we made a scan of the heat flux. We made a scan into fast ion temperature and computed the heat flux, and this gave us this result here. So the 20% increased heat flux that I showed you just in the last plots gives these 2 points here at about 2.5. So it's clearly that they are in the regime of close to the critical gradients. If we vary the gradients to 30% or 40%, we see we have this sharp increase. So we have a very stiff profiles. The nominal case is indicated by the dashed black line here. So you can see it's clearly well in the regime of the critical gradients, or it's well below the critical gradients. The linear estimate of the critical gradient is shown in the dashed red here, and you can see it seems to be slightly below the nonlinear prediction. Now, due to the fact that we are this close to the critical gradients has complicated this study, in particular the resolution scans. And this leads me to the last slide here, which is just how we have been trying to carry out these resolution studies. Now, because of the fact that we are marginally stable, so we are close to the critical gradients, as well as we have this feature of the NZT and this fast frequency mode, makes it very difficult to really find a good set of grid parameters, because by simply changing the grid parameters, we get one of these effects, and then we have to somehow change our input parameters in order to get something that we can actually simulate. Now, the current strategy that we have is to take a case at a much larger gradients and try to get some kind of a baseline of what our grid parameters should be. So to summarize, now in this project, we are working on predicting the turbulence in JT6 using one of the scenarios. In this case, it was high performance scenario 1. When we did the linear simulations, we found that we have really a vast range of electrostatic and electromagnetic modes. And we found out that we need to include all four species. We need to include magnetic field fluctuations and a large value of beta. Now, due to the fact that we have these many effects, many different modes, and in addition that we are not simulating experimental data, this has led to many different difficulties that we have and features that we have seen in our simulations. First of all, we saw that if we take the nominal parameters, we get very low heat flux, much lower compared to what we expect. When we try to increase the heat flux by increasing the gradients, we got the non-zonal transition, meaning that the heat flux do not saturate. And experimentally, this essentially means that we're going to have near infinitely stiff transport. So whatever heat flux, whatever power you give in, you won't change the gradients because of this very high heat flux. And finally, we also discovered this high frequency mode. So we have the fast ions resonating with a very low and high frequency Y mode, leading to a case where all of the heat flux is essentially being carried by the fast ions. And this has potential consequences on the efficiency of MBH, because we do not want the heating to go through the fast ions, but instead we want it to stay with the main species. Due to these various effects, the resolution study for this case is still something that is ongoing, and it's being complicated simply by the fact of these various effects that we can get even by simply changing the grid parameters. Now we hope the goal with this project is in order to create a template that can be used for future turbulence modeling in reactor-relevant regimes, as well as such as ITER and other JFRS scenarios, and really create a template for high beta simulations. Thank you for your attention, and I'm welcoming any questions now.
Thank you very much. Okay, now the question, comment, please. Please.
Okay. Alvin, thank you very much for presentation. I mean, one can expect that the results on the inclusion of fast ions will strongly depend on their concentration and their temperature relative. Yep. So, did you make some scan, or how do you get these numbers? Or what was your when you fix? What was the physics behind? So,
yeah.
So some parameters. Yeah. Thank you.
Yeah. So we got profiles for the fast ions. They are these predicted profiles that were computed with this suite of codes I was mentioning in the very beginning. So yeah, this one, Topic, Sacom, and Tosca. So this suite of codes were used to predict the profiles. And so we have the equilibrium, but we also have the fast ion pressure essentially coming in there. And then we took that and we modeled them with this simple Maxwellian. But yeah, as you see, if we simply take that, we get this resonance. So it's clear that we somehow have to change that, and this is what we then did later on with the linear simulations. We did a scan in the fast time parameters, and then we did a similar scan in the nonlinear simulations to see how do we actually remove this mode. Because if the mode is there, we cannot really simulate anything, but we have to remove it in order to get something that is actually where it's possible to draw any conclusions on what the transport or what the heat flux actually is.
Thank you. And what was the concentration roughly? Just so.
It was 3%, I think, compared to the electron. So I have the 0.03.
Thank you. Thank you very much.
Okay. Any other questions, please? 他にはないな。Okay, so I have one question. So in JT60 essay parameters, beta is 2.7%, right?
Yes, yes.
And later you discuss, some kinetic ballooning mode or something is beta is more, like 7%. And this is just far from the JT60 nominal parameter.
Yes, right? This is just to illustrate, because we don't want the parameters to be in the KBM limits. So we have to make sure that what we're starting with is at least below the KBM threshold, and that was one of the points with these scans. So we just wanted to sort of find out where actually is the KBM limits here.
And another question is if you just change to the temperature gradient, then you observe the very large heat flux.
Yeah, exactly. So when
is this due to ETG or short wavelength mode?
This is so this runaway is due to the non-zonal transition. So this is due to the fact that the zonal modes are not able to saturate the ITG. So we have many ITG turbulence here, and once you have this NZT, so the non-zonal transition that is happening if you keep a large value of beta and you have a large value of the gradients, and in that case the zonal modes simply cannot saturate the turbulence, and that leads to this runaway.
So this the simulations beta is 2.7%.
2.7%, exactly.
Okay.
Exactly. But then we had to decrease it. So like once we increased the gradients here, we had to lower beta to get into this green, so to say, region, so underneath this curve, in order to get something we can simulate. Otherwise, we're just gonna have a heat flux that is not saturating. So as we increased our gradients, we also lowered beta.
Okay.
So right now we are roughly at 90%, say, of the nominal value.
Okay. So when you change the temperature gradient, so
yeah.
So in this case, you don't recalculate the MHD equilibrium itself.
No. So the properly that should be done, but that I will also slow down this. So this is just in order to get an understanding of where is maybe the more correct parameter set, say. To do it then really properly, yes, you should recalculate your various profiles as well as the equilibrium.
Yeah, in this case, beta value is relatively high, so probably shuffle shift or something may change.
Yeah. No, that's true. That is true. But yeah, indeed.
Okay, thank you.
Okay. Any other questions? No. Okay, if not, thank you very much.
Thank you.
So we shall move to next speakers. Dr. Gutierrez.
Hi, hello.
Okay.
So let me share my screen.
Yeah, please.
Okay, so hello everyone. My name is Julio Gutierrez from the Barcelona Supercomputing Center. First of all, I would like to thank the organizers for giving me the chance to present our work here at this workshop. And of course to IFERC, CSC, and to all JFRS1 staff to give us this great resource that we can use for our simulations and also for all the technical support given during this project. So as you can see here, this is a collaborative project between different people and different parts that they all contribute in one way or another to the final goal, which is the initial study of tungsten metal from linear scaling Dft calculations. So I will start with a very brief introduction of, first of all, why we're interested in tungsten. This is, I guess you all know all this, but this is because tungsten is one of the reference plasma phasing materials. For example, the ether diverter is going to be made of tungsten. And this is because this is a very strong material. It has very low yield, and it is essentially the metal with the highest melting point in the periodic table. But during reactor operation, due to the heat fluxes and neutron irradiation, defects are going to be formed in tungsten. So that means that the initial properties of the material will change, and we, after some time, may end up with a material that has different properties than the one we had in the beginning. And we want to understand what's going on and why, how those changes will affect the operation of the reactor. Typically, when we model materials at atomic scale and we want to see defects, we base our simulations in two different models or scales, approximations. First of all, are quantum mechanical methods, which are the most fundamental ones. They are very accurate, but they are also expensive. So that's the reason why we can only simulate very small systems, and we can only model very small defects in those systems, so due to the limited due to the size and all this high expensive computational cost. On the other hand, if we want to make something a bit more affordable, we go typically to classical methods, in which we just model materials based on second Newton's law. This is much cheaper and allows us to make much larger models, but the main problem is that we rely on interatomic potentials that sometimes they are not as accurate as we wish because they have to be fitted for one specific material, structure, and property, and extrapolation is not always straightforward. And the other issue is normally the availability. So we have interatomic potentials for many pure elements, but if you want to work on multi-components or you want to extrapolate a bit far from what the potential has been designed for, then you can get in troubles, and this is not going to be that easy, So we are developing this method that we call linear scaling or large scale DFT. So first of all, we call large scale DFT to using DFT calculation to simulate models with thousands of atoms. As I mentioned before, ab initio DFT calculations are widely used to simulate materials because they essentially are based on laws of quantum mechanics. So based on theory, we can simulate nearly any element in the periodic table with very high accuracy and very high transferability. Because the only difference between one element and the other will be the number of electrons. So we can essentially simulate nearly any element with very high accuracy. But the problem, as I mentioned before, is the very high computational cost, or actually the very poor scaling. So DFT calculations, they scale cubically with the number of atoms or electrons in the system, but in practice means that we can only afford simulations of structures with few hundreds of atoms, like 200-300 atoms would be already starting being large. So in order to make larger simulations, as you see here in the graph, on this side we have quantum mechanical methods that are very transferable, very accurate, but we can simulate structures with small size. If we want to go to larger size, we typically go to semi-empirical methods or to classical methods. The main issue of that is, again, transferability. Although we can make some systems that are larger and more complex, then simulations cannot be that accurate. So this method we are developing, this linear scaling DFT or large scale DFT, we believe is nice bridge between both methods, in which we can get almost DFT accuracy, and we can reach very large size, much larger than the ones you would get with normal DFT. So this is a nice bridge between both sides and both methods. Of course, having the chance of simulating larger models give us possibilities to build more complex structures and to get better statistics and better models, or models that are closer to the real ones. Also, we can access quantum mechanical properties that are not accessible in classical models, like we can study electronic structure, excitations, charge transfers, or those kind of effects that they are very important in materials. And of course, we can use those methods to validate the empirical models, because if you want to make something large, then you must go to semi-empirical or classical models, but you cannot validate against classical DFT because you cannot simulate such a large system. So this could be used to validate the accuracy of classical models. So for these calculations, we use so-called linear scaling DFT. So I will go briefly a bit through the theory. So this is based on Walter Gong's Nielsen-Ness principle that says that electronic properties, they only act locally. So if we consider interactions between electrons only within a threshold radius, so we truncate all these interactions, then we can build directly the algorithm on the density matrix, and we avoid the diagonalization, which is the part that scales cubically, and this is the part of the algorithm that takes most of the computational cost in large systems. So we end up with a system that scales linearly with respect to the number of electrons, which means that if we double number of electrons, then computational cost will be also double. For this, we use a code called BigDFT, which was partially developed at our center. This code uses a localized basis function that is based on wavelets. Wavelets combine somehow some of the interesting properties of plane waves and Gaussian orbitals. So they are compact, they are orthogonal, and they also allow for systematic convergence. We use an adaptive mesh for the system, so we have a finer mesh closer to the center of the atom, and then a more loose mesh farther away. And we can use this basis set to simulate any boundary condition or any geometry. So we can use it for freestanding molecules or clusters, wires, surfaces, and also to three-dimensional periodic systems like crystals. This method has been widely used in the last few years, especially in non-metallic systems, so insulators, semiconductors, molecules, like biomolecules, but to work to simulate metals is rather new. So there are not many people working on this. Here I'm just summarizing some of the key parameters or the computational setup we use for the simulation. But just to give you an idea of how it works, of course, I will start saying that metals are challenging to simulate. They are much more difficult to semiconductors or insulators. And this is because when you have a finite energy gap, like in semiconductors, then the density matrix will decay rapidly because you don't have electronic states at the Fermi level. And that will help to get nicer, faster, better convergence. No? On the other hand, if you're working with metals, then you will have states at the Fermi level, and the electronic localization is not that obvious, not that easy. So the density matrix will decay more slowly, and these systems are very hard to converge, if not impossible. So what we do here in order to improve the convergence, or to get everything running a bit faster, is first of all, we use more support functions. So we calculate not only the electrons that are occupied, but also some of the unoccupied states. And we add those super functions, and we saw that that helped the convergence quite a bit. Also, we add some finite electronic temperature, and that also helps with the convergence and makes the things a bit faster. The other issue is that, of course, these calculations are expensive, so we need very large computational resources to run them. And this is because, okay, these methods, these linear scaling methods, they are more computationally expensive, but they scale well. No? So they are really worth it, or they are the only way if you want to run very large systems. But if you want to run systems that are within the range of sizes that you typically tackle with standard DFT, then these calculations are very, very expensive. So what I'm going to show, or try to show now in the results section, is our comparison between linear scaling and traditional DFT, and if it's possible to simulate metallic systems, or what is the accuracy we get from our calculations. So now going into results, I will start showing some scalability and convergence tests in the beginning. Then I will discuss a bit on the formation of defects in tungsten. Then I will introduce the pseudo-fragment approach. That is an approach that we are testing to reduce computational cost. And I will end with some models of the electronic structure of tungsten. So first of all, going into comparison between linear scaling and standard DFT. Here on the left-hand side, you see this graph where we have the energy versus volume, which are these curves here. The linear scaling DFT are these lines here. Basically, you can observe that the trend is pretty much the same than with standard DFT. There is a difference in the total energy, but variations are pretty similar, which means that we got good agreement. If we look at the pressure versus unit cell size, we also found perfect agreement between standard and linear scaling DFT. If we look at electronic structure, or electronic density of states, we observe again that there is perfect agreement between linear scaling and standard DFT. The only disagreement is here above the Fermi level, but this is because linear scaling or the support functions in linear scaling, they are not optimized for the unoccupied states, but in the region we are interested, we get perfect agreement between standard linear scaling methods. If we look to the computational cost, here on the left graph, we see the wall time as a function of the number of atoms for pure BCC tungsten. As I mentioned before, this purple line corresponds to cubic scaling DFT, to standard DFT, which you can see here that computational cost is relatively low if you are with small cells, but as soon as you increase the size above 500 or 1000 atoms, computational costs increase cubically, which makes simulations with thousands of atoms or even more than 500 atoms quite unaffordable or quite expensive. On the other hand, if we look at this blue line here, blue squares that correspond to the FOE method, which is the pure linear scaling method that we use in big DFT, we can see that the behavior is linear, not this straight line. And this makes simulations with even 2,000–3,000 atoms affordable. That is something that we could not reach with standard DFT. On the other hand, of course, if you want to simulate system with less than 500 atoms, then it's not that worth it. So computational cost would be almost double compared to standard DFT. But if you want to go to large systems, linear scaling is probably the only way. If we look at scalability for one test atom with 1024 atoms, and we increase the number of cores, we find very good scalability. So this is the straight line will be the perfect scalability. And even for almost 8,000 cores, we get 74% scalability. This is just for 1,000 atoms. So we have to keep in mind that in our work, we are running systems with more than 3,000 atoms. And if we expect that if we increase the number of atoms, then scalability will be consistent, and we could also increase the number of cores with very high efficiency. Now looking at the total energy convergence, we essentially start with very small cell, and we increase the size progressively, and we compare the total energy as a function of the number of atoms, taking as a reference the value from the larger cell we have simulated. So this is just to show that we really need large systems to get energy convergence. So if we get systems with few hundred atoms, then the error would be quite large. But if we have systems with around 1,500 atoms or 2,000, then we get the energy that is nicely converged. As you know, we are not working on perfect BCC tungsten, but we also account for the formation of defects and their stability. Here we have studied the two most typical defects that they are formed in tungsten, which are vacancies and interstitials. Vacancies is just you take a cubic periodic cell and you remove an atom from the center of the cell. Here we observe that this has a not very large effect in the structure, but still has some. So we observe that if you remove an atom from the center of the cell, of course, atoms in the first and second neighbor position will shrink their bonds. That will be around 1%, but this deformation will not go much farther than that. What means that we can probably simulate single defects or single vacancies within a small unit cell, or relatively small unit cell. On the other hand, if we look at self-interstitial, which is you put an atom in the middle of a perfect BCC cell, this, of course, will have a large effect in the cell. So you observe here that we put one interstitial in the 111 position of the BCC structure, and this has deformed all this region here, which correspond to around 4 or 5 unit cells, which means that if we want to simulate or to understand the effect of one single interstitial within a 3-dimensional periodic structure, we actually need a large structure to avoid self-interaction between defects. Now, if we look at the formation energy in this graph here, so here we have the defect formation energy versus number of atoms. Here on top, we have the formation energy for interstitials. Here on the bottom for the vacancies. These color regions are values that we have taken from the literature that actually they have been done with slightly different methods, and all of them with cells that are not larger than, I think, 200, 300, 400 atoms. But still, this is what we have and we can compare with, just to have an idea on where we are and how this work compares to other ones, to available ones. And this X here and here are the values we got with the cubic scaling version of Big DFT. So first of all, if we look at the numbers we get here on the left-hand side, so for the small unit cells, we observe that, as I showed before, since the total energy is not well converged, then these values are not that accurate. While if we increase a little bit the size of the system, like this region here, then we observe that we get values that are closer to what we were expecting to get now. In this case, we see that probably vacancies should be converged within this region here already in terms of size, because they don't have such a strong self-interaction. On the other hand, for self-interstitial, we expect that probably this region here will start the convergence, or the part where self-interaction is not that strong. On the other hand, if we look at structures that are very large, we observe that values deviate from what we were expecting to get. And although here there is some sign of convergence, we are still far from the values we were expecting. So we believe there are several reasons to explain this behavior. First of all, is that when we increase the number of atoms to 2,000 or 3,000, then the degrees of freedom increase dramatically, and relaxation algorithm, they don't perform that well. So it's very hard to go to very accurate relaxation and low forces in very large systems, and these calculations are very, very expensive, so we didn't want to iterate this like very, very long. And these models within the large cells, they have stronger forces than the ones here that are very nicely converged. So it's almost 1 order of magnitude of difference here. And we expect this will have some effect. Still, the relaxation energy for one vacancy is between 0.3 and 0.1 eV. So this is still far from the reference. But yeah, we are still trying to figure out what's going on and how can we improve this. One of the things we are doing is increasing the accuracy from the computational setup. And we are running some tests now. We finished some time ago. And the good thing here is that increasing those parameters or playing a bit with the mesh, making a more finer description, give us better results, or results that are actually in the range that we're expecting. But of course, this has a higher computational cost. So this is always a trade-off between how accurate you want to get your numbers and how much computational cost you want to invest, or how much you can invest into these calculations. On the positive side, we have seen that if we take one system, one reference system, and we make 2 vacancies, for example, in 2 different sites, we observe that the formation energy is the same, what means that formation energy for vacancies are consistent, at least within a fixed size or within a fixed cell, which is good. Also, we observed one interesting property that has already been proved in PCC metals, which is the negative binding energy between defects, what means that making a second vacancy will be more expensive than making the first vacancy in the system. And we also found that the formation energy of the vacancy in the first neighbor position will be slightly cheaper than the one in the second neighbor, but of course more expensive than the very first vacancy we made. Now I will talk a bit about this method we are testing, that is we call pseudo fragment. That is a method that is designed to decrease computational cost of these simulations, which is especially important in very large systems. So for this, I will just show you a very simple example, starting with a water molecule. So we start with what we call the template, that in this case will be made by 1 oxygen and 2 hydrogen atoms. And we optimize the support function for the template. No? So when we get this template, which is the fragment or the template for a fragment, this has properties that allow the replication and translation of the model. So in this case, you can just take one single water molecule and you can replicate this in space, you can rotate, and you can simulate a group of water molecules. Here, then you have basically 2 options. You can use support function that you generate for the template as a basis set and optimize only the kernel, which really gives you a much faster convergence, but the accuracy will be a bit lower. So you have to always to assess how much accuracy you want to get. The other option is to take this model with the initial template and use it as an input for a full simulation. So you optimize super functions starting from the previous super function that will give you basically the same results than starting simulation from scratch, but it will converge much faster. Generation of the template will be cheaper in the beginning, so you will save computational time. One very simple example going into materials, just to show how this definition of templates and the fragments work. Here we have a graphene layer that we have doped with one single silicon atom. If we define just 2 fragments, so we consider fragment, say, number 1, 2 neighbors surrounding the silicon atom, so this orange-red balls, and second fragment will be everything else. Then this will be, of course, a very rough approximation, and the error that we will get comparing this fragment approach with normal standard calculation will be very high. On the other hand, if we increase progressively the number of fragments, as you see here or here, so we define more and more fragments as a function of the distance from the vacancy or from the defect that we have created or from this doping, then of course the simulation will get a bit more complex, but computational, the accuracy will be much better, no? And there will be a point that we actually get a very nice convergence like here. And these are probably values that we can assume and we can go with this fragment approach. So it is always good, or it's always important to look at the geometry of the model you are working with and define the number of fragments and the regions accordingly. Of course, we have done this for tungsten. So here on the left-hand side, you can see the cross-section of a body center cubic tungsten, in which we have defined fragments as shells that they depend on their distance from the vacancy, which is here in the middle. So here you have here different fragments with different colors. This is just a plane, a projection, but we do this in 3 dimensions, so it would be like a spherical shell. If we start with a relatively small structure with 686 atoms, we use the frag optimization, which means we start with the fragments to make calculation faster, but we optimize the fragment. We optimize the super function starting from the initial fragment. We observe that to get nice convergence and also to get values that are same as the ones we get from the full calculations, we need to define 10 fragments. So we need to define 10 shells or 10th order nearest neighbor from the vacancy we had here in the middle. On the other hand, if we just use the normal fragment approach and we don't optimize super functions, we get, of course, a larger error, but still these are milli-electron volts per atom, and this error will be below 2. So this is still not too bad, and calculation will be much faster. Then we use these templates we have generated for the 686 atom structure that we have seen is enough to simulate or to model this single vacancy, and we use that to simulate a larger structure with almost 1,500 atoms. No? In this case, of course, if fragments or the number of fragments is not nicely defined, you get inaccurate results. But if you start with, if you use number of fragments that is converged, like something between above 10 fragments, which is around 8 angstrom distance from the vacancy, then the errors are very, very low. And computational cost is around 1/2 of the one we were getting if we wanted to do the full calculation. And these errors here can just give you a rough number, but they were between 0.1 and 0.2 milli EV per atom, which is like very, very small error. And we increased the efficiency by factor of 2. So I think these are positive results for the defects, but also we have used these fragments to calculate perfect structures. So in this case, everything is much easier because we have a perfect BCC model. So all atoms are actually equivalent within the cell. And you can just define one single fragment and make everything easier. And we have also looked into electronic structure of the material. So here I show the total and projected density of states for pure tungsten with different number of atoms between 1,500 and 3,500. For the large systems, we have used the pseudo-fragment approach, and we have compared the results we got from pseudo-fragment approach and also from normal calculation, also standard calculation starting from scratch. And we have seen that, again, as I said before, the results are pretty similar, and computational cost is much, much lower. Of course, different properties, they will converge differently. So we can actually get very, very nice electronic structure with few thousand atoms, while if you were to calculate, as I showed before, energy formations or vacancy defects and those kind of things, they are more complex properties and they probably converge a bit later than this electronic structure. So you may need larger cells, or you may need to tune the parameters a bit more. So of course, different properties, they behave differently. But as you see here, if we increase progressively the number of atoms in the system, the electronic density of states gets smoother, or I would say better, but you will see comparison later. Especially if you compare states here at the tail or here at the two main peaks here in this region, also states at the Fermi level, you see that everything gets smoother and more nicely converged as we increase the number of atoms in the system. We observed as we expected that the main contribution is coming from the electrons. And this effect here of the convergence is somehow comparable to what you would do if you increase the K points. So if you have a better defined, a finer K point grid in standard Dft calculations. And this is the farthest we have gone for now, but we may go farther in the future. Of course, we have compared this with standard Dft, and we have compared these are our calculations here with linear scaling Dft with 3,456 atoms. Of course, we do calculations at the gamma point, so we don't use any K points because these calculations, these models are done for very large systems, and we don't really need to use also K points in these calculations. But we have compared this with a primitive unit cell with many K points that has been calculated with plane wave Dft, with quantum express in this case. And also we have done similar calculations, or our collaborators, with GW calculations. And we have also compared this with experiments. So this blue line here is experimental data that has been taken from X-ray photospectroscopy. So here we can see that our linear scaling Dft is quite comparable to what we have found with other Dft or ab initio methods, that they also reproduce quite nicely all the main features that they were observed or they were measured from experiments. So just to summarize what I have shown, what we have done so far, we have shown that big DFT can be used to calculate metals accurately, overcoming the size limitation of standard DFT. So you have to take into account that most of these calculations so far, they have been done with few hundred of atoms, and we have gone one order of magnitude beyond that. We have done for first time large-scale calculations of vacancies and self-interstitials in Tungsten with linear scaling big DFT. We have seen that for now we need at least thousands of atoms to get convergence, but of course it depends on the property you are trying to get, or that you are trying to simulate, or the model you are working with. We have seen that we can get very accurate electronic structure density states, and that the pseudo-fragment approach works quite well for this. But of course, this is always a trade-off for the pseudo-fragment and for all input properties you want to put, input parameters you want to put into your simulation. And of course, it always depends on the accuracy you want to get and the computational time you can put into these calculations. And of course, more testing is required. So we are still working on this. This is ongoing work. And there are still some things we want to understand. We want to work a bit more on this and to see how far we can go with these models and how accurate they are compared to standard DFT. In terms of development, we have developed a calculator for the atomic simulation environment. This is a very widely used DFT or ab initio or atomistic-based interface to run models and to pre-post processing of structural models and atomistic simulations that can be used with many codes, and we have implemented our code also within that framework that will increase the usability of the code and will make this available to more users. We have also started classical simulations on thermal conductivity in defective tungsten, which is something we are running in parallel, and that will be one of the main focus in the next project we are going to run also in JFRS 1. We have also started some work on doped and alloyed tungsten. And of course, we have initiated benchmarks for the next project that we're already implementing at JFRS 1. And that's, we are trying to simulate similar models, but with implementing new techniques. In terms of dissemination, we have published 2 papers so far, and we have 2 more in publications, 2 more in preparation. We have presented this work, or all things that are related with this work, in 13 conferences and workshops so far, all of them international. Next steps, we just got approved the next project for this 2022 term, in which we are going to study thermal and mechanical properties from molecular dynamics and lattice dynamics calculations. We are going to develop interatomic potentials for tungsten and tungsten-based compounds based on machine learning. And again, we use linear scaling big DFT for the validation of these calculations we'll do. So before finishing, I would like to thank of course, our funders, to all JFRS 1 at IFERC CSC evaluators and technical support, which has been great over this year, especially in the beginning of the project, trying to set up all this code and optimizing all the performance. And to all the collaborators, of course, to our team, and to all of you for your attention. Thank you.
Thank you very much. Okay. So the question and comment, please. No questions. Okay, please.
Thank you for interesting talk. I am not the expert for this kind of analysis, but the simulations. But I think it's you mentioned about your result will be applied for the material properties in futures. I think MD is doing some, but what kind of a material property are you expecting to apply, such as ductility or DBTT or any such properties? Do you have a comment?
Yeah, sure. So yeah, okay. First of all, we're trying to understand the structure at the atomic level of defects, and to validate. Okay, so the big DFT part is, I would say, is more a proof of principle study, and try to see how accurate is the method. Then, of course, we want to apply these large models and to take advantage of the method we are using to simulate some properties. So far, we are mainly focused on thermal properties, so thermal conductivity. So we are trying to understand how these
thermal
defects,
conductivity.
Yeah, so those we can want to understand how these defects they affect thermal conductivity, specifically the lattice thermal conductivity, which is what you can get from these models, from classical molecular dynamics or non-equilibrium models. But we are also going to implement in this term lattice dynamic calculations. So with this method, you get access to, of course, thermal properties, but also you get mechanical properties. So from mechanical properties, what you get is the elastic tensor. So from the elastic tensor, you can get properties like Young's modulus, bulk modulus, Poisson ratio. And of course, you can use those numbers that you get from ab initio to build the potential to run classical MD. And from there, you can do essentially any testing. Like you can make tensile deformation or stress strain, compression test. The ductile to brittle transition is probably more challenging. So I wouldn't know how to address that part. But in principle, we can make properties like stress, strain, or compression, tensile, or any kind of deformation.
Okay, thank you.
Thank you. Any other questions? I have one question. Your method is applicable the phenomena such as grain boundary embrittlement by helium irradiation on tungsten?
Yeah. So I think this is one of the main advantages we had with this method, and this is something we wanted to look at when we get all these fundamental issues sorted. So if you want to look at a grain boundary, especially when you're working with standard DFT and you are limited to, I don't know, 200-300 atoms, and you will have a cross section of around, let's say, 10 or 12 angstrom, which is like very small, then the interface is very challenging because you have to compensate the mismatch between two grains, the lattice mismatch. And of course, the size and the amounts of defects and things you can put in the grain boundary, for example, if you want to put a bubble, a helium bubble or something like that, then you will be quite limited by the size of the cell or the model you can simulate. So one advantage of having these models with large size is that we can make a very large interface. So we can build a model with, I would say, 30 to 40 angstrom cross-section, and we can simulate those grain boundaries from DFT, or even make polycrystalline or nanocrystalline structure, which is something that, of course, you cannot do with standard DFT, and you must do with classical MD because of the size. So if you want to make like a polycrystalline, you need a large cell. So yeah, one idea would be to take advantage. That would be one possible application of these models, to take advantage of the large size to build either large interfaces between grains or polycrystalline models.
Okay, thank you very much. Any other questions? No? Okay, thank you very much.
Okay, thanks.
So we can continue to next speakers. Next speaker, Dr. Seto, hybrid Poisson solver for annual tokamak edge diagram simulations, please.
Okay, please wait. So can you hear my voice?
Yes.
And can you see my presentation now?
Yeah, okay, no problem.
Okay, thank you, Chairman. I'm Haruki Seto from QST, the principal investigator of Project H. So I'd like to thank IFERC CSC for giving me this opportunity. And title of my talk is Hybrid Person Solver for Full Annular Tokamak Turbulence Simulation. And due to the machine spec of my laptop, I will turn off my camera. Sorry. So this is the outline of my talk. First, as an introduction, I briefly explain about ++ code and objective of the TOC project. Second, numerical scheme for full annular tokamak edge simulation developed in this project is briefly reviewed. Before reporting the result obtained in IFERC CSC cycle 2021, I will report the impact of fruit drying assumption in low and ideal ballooning mode as a last term of my presentation presented in the last CSC workshop here. After that, I will report the result of production run of pedestal collapse simulation in full annular torus domain in 50 circular geometry and preliminary test of full annular torus turbulence simulation in single null diverted geometry carried out in 2021 cycle, and then summarize my talk. About ++ is a plasma fluid simulation framework in curvilinear geometry using a finite differencing scheme. For tokamak edge simulations, about ++ calculates middle end and high end structures with high accuracy in complex boundary region in tokamak plasmas by using special coordinate systems. But as a side effect of usage of these special coordinate systems, fruit ordering assumption is required on person solver for resonant modes. It is well known that the fruit ordering assumption may not be accurate for low-end modes, especially in diverted geometries. And the project TOC is a 3-year project to extend about ++ framework for tokamak edge simulation, solving interplay between n equals 0 for resonant mode, low N MHD, and middle N and high N turbulence mode in diverted geometries. This is important for simulating current-driven elements, resonant magnet RMPs, full annular torus edge turbulence simulation, and so on. In the last workshop, the development of fruit ordering pre-person solver for low-end modes and some preliminary simulations were reported. Today, I will report the production run of full annular tokamak edge simulation with circular cross-section and the preliminary test of full annular tokamak edge simulation with single null diverted geometry. And about ++ calculate middle N and high N mode with high accuracy and cheap costs using both flux coordinate systems and field aligned coordinate system with shifted metrics for tokamaks. Now the left figure shows the computational domain of 1/4 annular wedge tokamak torus domain, and the color stands for the value of Poidal angle. For tokamak edge simulations, where the safety factor increased towards the last closed flux surfaces, numerical grid based on the flux surface coordinate needs fine Poidal resolution for parallel differencing. On the other hand, the computational grids in the field-aligned coordinate system is constructed by shifting the grid in the flux surface coordinates to toroidal direction by angle alpha. Alpha is relating to the local magnetic field pitch, and the grid is shown in the right. In this grid, parallel differentiation can be evaluated with the coarse resolution, since the grid is aligned to the magnetic field line. However, the cell deformation by magnetic shear degrades the numerical accuracy of radial differencing, since the shift angle or the value of safety factor changes radially. To resolve these issues, about ++ employs a field-aligned coordinate for differencing, for parallel differencing and binomial differencing. and employs a flux surface coordinate for radial differencing. The Poisson solver for calculating flow potential from vorticity in reduced MHD models employs a float ordering assumption to solve Poisson solver as 1D boundary problem in flux surface coordinate, as I mentioned in the introduction. However, the float ordering or neglecting parallel derivative may not be valid for n equals 0 and low n modes, especially in diverted geometries. Now the linearized Poisson solver for n equal n prime modes of vorticity in Fourier space with shifted metrics can be expressed with the following form, including the radial derivative in flux surface coordinate and parallel derivatives in field aligned coordinate systems. To define Poisson solver as a boundary problem in flux surface coordinates for resonant modes, the float ordering assumption is employed to neglect the parallel derivatives like that. And for Poisson solver for n equals 0 modes, so field aligned coordinate system is employed. This is because this is for the for Poisson solver for n equals 0 mode is defined as a boundary problem in field aligned coordinate system by using the toroidal symmetry property of the field to be inverted. In Project H, a new 2D Poisson solver defined in flux surface coordinate system with the standard flux surface coordinate matrix is developed in cycle 2020. This solver provides a self-consistent flow potential without float ordering for ON modes, but toroidal grid resolution must be fine enough to describe the toroidal structure of ON modes, since the parallel derivatives are divided into the toroidal and toroidal derivatives. And this solver employs the GM-less method for Kirchhoff subspace solver and the algebraic multi-grid method for preconditioning via PETSI and hyperlibraries. The workflow in a hybrid Poisson solver using both float ordered and float ordering pre-Poisson solver is summarized in this figure. The vorticity at the time step L and the flow potential at the previous time step L-1 defined in the field aligned systems are input as the right-hand side values and initial guess for PETSI solver. And these values are converted to the flux surface coordinate system in Fourier space. And the potentials are calculated by the 2D Poisson solver for toroidal mode less than and equal to n equal to n2D max. And the potential are calculated by 1D Poisson solver for toroidal modes larger than n2D max up to n1D max sequentially. And the flow potentials are at time step L are combined in Fourier space and is converted to field aligned coordinate system in real space as input. It should be noticed that the highest toroidal mode number solved by 2D Poisson solver and that by 1D Poisson solver are free parameters to be chosen carefully, and the hybrid Laplacian operator consistent with the hybrid Poisson solver is also important for numerical stability of simulation. In this section, impact of float ordering assumption in low ideal ballooning mode is reported as the errata of my previous presentation in CSC workshop. For linear benchmark following linearized ideal ballooning model consisting of vorticity equation, Ohm's law, and the equation of energy is employed. This simplified model is normalized with toroidal Alban unit, and the original BALT++ employs float ordering in Poisson solver for electrostatic potentials and in Laplacian operator for calculating parallel currents. The latter fruit ordering is for the consistency with Poisson solver. And a well-benchmarked equilibrium with circular cross-section, a strongly unstable for ideal ballooning mode is employed in this study. The linear growth rate of ideal ballooning mode are calculated as a fundamental mode of 1nth annular wedge torus domain in binomial direction for n modes, with following four sets of differential operators here. And in case 1, fruit ordering is employed in both Laplacian and Poisson solver as original but plus. So the parallel grid number is reduced to 64. In case 2, the fruit ordering is employed only on Laplacian. So that the parallel grid number is set to 512 for Poisson solver. In case 3, the fruit ordering is employed only in Poisson solver, but the parallel grid number is limited to 64 for numerical instability. In case 4, fruit ordering is not employed, so that the parallel grid number is set to 512. In the last workshop, the result of case 3 was reported as case 1 by mistake, and it was concluded that the fruit ordering assumption has little impact in this equilibrium. And now this figure summarizes the benchmark result with 4 cases in low n regime from n equal 5 to 8. From the difference between circle symbols and square symbols, it is found that the fruit ordering assumption in Laplacian for parallel current have large impact in low n regime. So here there is about 40% relative difference. And from the difference between the red colored symbols and blue colored symbols, it is found that the fruit ordering Poisson solvers for electrostatic potential phi has little impact in every low n regime. So the difference between the red colored and the blue colored circles and the difference between the red square circle, red square and blue square. So it should be noticed that the asymmetric usage of fruit ordering assumption, case 2 and case 3, can give disruptive numerical instabilities, and these cases are just employed for numerical experiment on fruit ordering assumption. The benchmark result of fruit ordered Laplacian and Poisson solver colored by red, and fruit ordering for the Laplacian and Poisson solver colored by blue from n equal 5 to n equal 20 are summarized in this figure. Here, the published benchmark results calculated by BALT++ and ELITE at n equal 20 are also plotted with the green circle for BALT, green for BALT++ and black for ELITE. So for high-n regime, the growth rate calculated with and without fruit ordering agreed well, so that the fruit ordering seems good for high-n regimes. And it is also confirmed that the fruit ordering free Laplacian and Poisson solver, case 4, can capture ideal ballooning mode eigenfunction correctly, as is shown in the below figure here. On the other hand, the fruit ordering gives large difference for low n regimes, which is mainly due to the fruit ordering in Laplacian for parallel current, as is shown in the previous slide. It should be noticed that the previous BALT++ benchmark overestimates the growth rate in low n regimes, and the present fruit ordering free scheme can suppress this overestimation to some level. And the test of fruit ordering free scheme against low n linear resistive ballooning mode in single null diverted geometry was also finished, which was reported in the last CSC workshop. So I will report the production run of pedestal collapse simulation in annular fruit torus domain in shifted circular geometry for checking impact of domain length in toroidal direction or usage of wedged domain. So in this simulation, the four-field reduced MHD model describing resistive ballooning mode and drift wave instabilities and shifty circular geometry marginally unstable against ideal ballooning mode are employed. The simulation setup but grid resolution as the same as my CPP paper. For scan of binomial domain lengths in pedestal collapse simulations, following three domains are employed. So full torus case, half torus case, and quarter torus case. In these cases, grid widths in all directions are set to the same by changing the number of the grids in binomial direction in accordance with how many, so the domain size. Here, the full ordering free Poisson solver and Laplacians are employed up to n equal 4 modes, and the full ordered Poisson solver and Laplacians are applied for n equal 5 to 80 modes, and the toroidal modes more than 80 modes are filtered out by low-pass filter. So in this setup, the most unstable mode is n equal 32 mode, so that taking it up to n equal 80 mode is adequate. The time evolution of energy loss from inside of pressure gradient peak in these three cases during pedestal collapse are summarized in this figure. So initially unstable mode sets the pedestal collapse onset at t equal 200 Arben time, but energy loss increase slower for full torus cases compared with quarter cases and half cases. So now the right figure is the time evolution of perpendicular kinetic energy in quarter torus case. The vertical axis is the toroidal mode number, and the horizontal axis is time, and the color shows the amplitude of perpendicular kinetic energy, respectively. So in quarter torus case, initially unstable mode strongly excited and directly drive the collapse. And now bottom figure shows the time evolution of perpendicular kinetic energy in full torus case. So in full torus case, low n mode around n equal 1 modes are generated via nonlinear coupling between initially unstable modes, and collapse is triggered by downshifted mode around n equal 20 to 30 modes. And this is the top figure shows a snapshot of 3D structure of electrostatic potential during pedestal collapse around t equals 330 in full torus case. So the global n equal 1, m equal 2 structure and the very fine filament structure coexists in this simulation. Now this figure summarizes the energy loss after the pedestal collapse. So in all cases, energy loss enhancement by interplay between zonal flow and turbulence is observed, and the energy loss level saturates to similar level. And the perpendicular kinetic energy spectra in full torus cases in the bottom, and the turbulence burst occurs periodically after the pedestal collapse. The left figure are spatiotemporal structure of equal-speed sharing rates at the top figure, and the spatiotemporal structure of turbulence intensity at bottom here. And the right is the for full torus case, respectively. So turbulence bursts with cyclic oscillation between zonal flow and turbulence are observed in both quarter and full torus cases, but n equal 1 fluctuation has global structure. Sorry. The structure whose peak is located at turbulence burst in full torus cases in this hatched region. So there is a little difference in energy loss level after pedestal collapse, but there is a difference in special structure fluctuations between quarter and full torus cases. And finally, I will share with you the preliminary test results of full annular torus simulation in single null diverted geometry. And this preliminary test employs the East-like single null diverted geometry. The grid resolution information is summarized here. So float-running free Poisson solver and Laplacians are applied on up to n equal 4 modes, and the fruit-ordered ones are applied from n equal 5 to n equal 18 modes, respectively. It should be noticed that if the fruit-ordered Poisson solver is applied to n equal 1 mode, the disruptive numerical oscillation instability occurs within few Alben time. The scale-separated three-field reduced MHD model is including simplified ion geomagnetism and electron hole effect is employed in this test. I will skip its detail, but non-sol and diverter physics are included. This is just a test for checking whether the hybrid Poisson solver makes full annular torus simulation possible or not. And this slide summarizes the initial dispersion relation of this simulation setup, and n equal 80 mode is the most unstable mode in this parameter. It should be noted that growth rates calculated with and without product ordering assumption agreed well with for n equal 4 and n equal 5 modes here, which means that using 2D Poisson solver less than or equal to n equal 4 mode seems to be appropriate. And this is the time evolution of kinetic energy spectra, showing that the kinetic energy grows in the reasonable manner. So initially, unstable modes linearly get excited in linear phase. So the peak is around n equal 18. And the low n modes get excited via nonlinear coupling among initially unstable modes. And the higher mode also get exciting via coupling among the initially unstable mode and low n mode. And finally, kinetic energy spectra reach to the nonlinear saturation phase, and zonal flow or n equals 0 component of perpendicular kinetic energy is strongly excited like that. Based on this preliminary test for numerical stability in full annular torus simulation with diverted geometry, full annular edge turbulence simulations in eta baseline cases is in preparation, partially under Dft collaboration between QST and Lawrence Livermore National Laboratory, which will be carried out in this IFERC CSC circle and will be reported in the next CSC meeting. And let me summarize my talk. Hybrid Poisson solver for full annular tokamak edge simulation has been developed. The impact of fruit-running assumption in low and ideal ballooning mode has been investigated again. And it is found that fruit-running assumption in Laplacian for J parallel has large impact on IBM growth rate in this case. And then pedestal collapse simulation in full annular torus domain in shifted circular geometry has been reported with the production run scale resolution. N equal 1 fluctuation has global radial structure during and after pedestal collapse in full torus cases. And finally, the preliminary test of full annular torus turbulence simulation in single null diverted geometry has been reported. It is confirmed that the hybrid Poisson solver developed in this work enables BAT++ code to carry out nonlinear full annular torus simulation in diverted geometry as well as shifted circular geometry. And the production run with eta baseline equilibrium is in preparation, which will be carried out in this cycle. That's all. Thank you for your attention.
Thank you very much. Okay, now the question, comment, please. No questions. Okay, please.
Yeah, I mean, thank you for presentation. I have a question. What is the scaling of one-dimensional Poisson solver?
I
Quite
have
often used in kinetic codes and
it's a good question. So the 2D Poisson solver is very slow compared with the fruit-ordered Poisson solver. I haven't checked it in detail, but maybe 100 times slower than the reduced the fruit-ordered simulation. For example, for calculating n equal 5 mode here, with in case 5, in case 1, so using reduced, using fruit ordering, both Laplacian and Poisson solver, this growth rate can be obtained by maybe the 10-minute simulation with 200 CPU, but for 2D Poisson solver, about 2 hours for 500 CPUs. It depends on problem. But I confirm that the 3D Poisson solver is fast enough to apply the production run scale grid resolution.
Okay, thank you very much. I mean, it's very difficult to compare in our cases because in kinetic codes we are using a few millions of grids and hard to. But I mean, it would be very nice to compare with existing models to say, okay, this is your scaling, and to compare to other models, because Poisson model is usually code probably. Just to say what is the advantage, what is the disadvantage, I think. Because thank you very much. Yeah.
Oh, thank you.
Okay, any other questions? I have one question about, you say X point configuration, especially this 2D Poisson solver is necessary for numerical stabilities. But
yes.
What is the difference between the circular and the X point case? What makes difficult to numerical stability for this case?
One important property, one important difference between the circular case and the X-diverted case is the mesh accumulation around the X point in diverted geometry. So in diverted geometry case, so about to have a constraint which have about to have to use the orthogonal grid. So the grid width around in parallel direction around the X point become very narrower and narrower. And in that case, the condition number of Poisson solver for diverted geometry case become worse and worse compared with the shifted circular case. So, and also the metric have the strong toroidal variation, and it also degrades the numerical stability of fruit-ordered Poisson solver.
Okay, thank you. Any other questions? If not, thank you very much.
Thank you.
Okay, so then we shall conclude. So Nakajima-san may conclude and closing talk.
Okay, so this is a very short closing remarks. Firstly, thank you very much for attending this workshop, and especially thank you very much for presenting interesting talks. I recognize that the how to say good progress of the simulation projects are indeed obtained, and although the JFRS1 to use the JFRS1 is useful for such simulation project. And so additionally, I hope that collaborative work with either Jet6SA and also demo will be promoted further in terms of JFRS1. Okay. So thank you very much for attending the meeting and presenting the interesting talks. Yes, you say something.
Yeah, thank you very much all for participating in this workshop. Yeah, as Nakajima said, we close the meeting. So yeah, it's now just lunchtime in Europe and dinner time in Japan. So okay, let's go to lunch and dinner. So yeah, okay, goodbye.
And this recording is uploaded to YouTube or something? No.
Yeah, probably it will be uploaded on the Fusion channel.
Okay.
Probably.
So I think presentation will be uploaded on the IFERC website, right?
Yeah. Later.
Yes.
Okay, that's all.
Okay, that's all. So, say goodbye.
Thank you very much and goodbye.
Bye.
Thank you. Goodbye.
Bye.
Goodbye.
Thanks, bye.